Hey, what's going on, guys? Welcome back to another stream on the Mizu Study channel. I'm sorry for a bit of the delay there. I had to go out and run some errands real quick, yeah. But sorry, I'm back now. I'm ready to go. We have a big revision day today, ultra revision day. Come on, let's get it. Let's do this. Inshallah. So what we have today is yesterday we did the titrations. We finished them off. We spent like 2 hours on that. I need to do 1, 2, 3, 1, 2, 3. Oh, yeah. So I've learned, so I have my quotes ready as well. I have overview here. Yeah, so hopefully everything goes to plan. So I'm just gonna mark all the chapters I've done past papers for so I don't do them again because I'm good at them enough. Good enough. Alright. So we're gonna be doing sorry. Bro, if there's a will, there's a way. I'm telling you. This life, bro. This life's temporary, bro. So if there's a will, if you know what to do and how to do it, you can get it done, bro. That's why I'm not stressed out right now. Other people would be like crying right now. I finished the course basically. You get me? So don't think that this guy's like no, cause I've been there. I've done that, bro. I've been there. I've done that. Yeah. I just. Sorry, I just need to organize my notes real quick. Alright, we need to start off with organic 4. So my schedule for today is organic 4 to 10, and then finish the rest of the chapters we haven't done. So VS3, PRT, so shapes of molecules, acids and bases, oxidation reduction, and test for adides, and then lab science as well, lab safety science as well. And then we'll do organic 4 to 10. Then we'll do 3 backbet quotes. We'll do Elizabeth Bishop. Then we're going to do Harlamabach, and we'll do a listing for Irish and French. And then we'll finish off with atomic 6 to 10 at sequences and series. Alright. I'll see if I'm in the kind of the lingo for doing chemistry, then I'll just do chemistry. Yeah. Well, we'll see how it goes. Oh man. Alright. I'm ready. I'm excited. I'm ready to go. Excited? Yeah, I'm actually excited because I want to achieve my goals. Alright. So let's go. We'll do the past papers as well. Yeah. So basically, aldehydes, ketones, carboxylic acid. So planar carbon is a carbon with a double bond and 2 single bond, or a triple bond and a single bond. Yeah. So what is the functional group of an aldehyde? So if you go to aldehyde, right? Aldehyde, I mean C double bond O single bond H. That is the functional group, right? So you have a carbonyl group. That's a carbonyl group. Yeah. Alright. So we see that we can see from the functional group. So what is a functional group? It's a group of atoms upon which the characteristic properties of homologous series depends. What is homologous series? A group of compounds which all contain the same functional group and successive members differ by CH2. Alright, we'll get onto that in a minute. But as we can see from their functional group, the aldehydes contain a carbonyl group. Exactly what I said, right? A carbonyl group is C double bond O, and the carbonyl group is polar due to the difference in the electronegativity values of the carbon and the oxygen. So if we come here, you'll see that if I have carbon and oxygen, the electronegativity of this is 2.55, and the electronegativity difference of this is 3.44. So if we minus them, that's 45. It's like 0.89, right? 0.89 is greater than 0.5, but it's less than 1.7. That means it's a polar covalent bond, right? Polar covalent in intramolecular. So inside of the molecule, the atoms are bonded with polar covalent bonding. So that means that this carbonyl group, yeah, is polar due to the electronegativity difference between the carbon and the oxygen, yeah. So Yeah. Oxygen, of course, which one has a higher electronegative? Yeah, so oxygen is going to be like delta negative and it's going to be delta positive. So remember we said pure covalent is the only one that has a temporary dipole because it's switching constantly. But polar covalent kind of has these like fixed kind of terms. So this is delta negative, this is delta positive. All right, fair. Now it says carbon is less electronegative. As a result, the carbonyl groups, there's dipole. As a result of these carbonyl groups, there's dipole forces of attraction between the aldehyde molecules. Uh, yeah, so this is intra, but dipole. So this dipole. I think this is also called London or something. I don't know. Right? But dipole, right? Forces of attraction, which are intermolecular. Intermolecular. So intermolecular means between molecules. Intramolecular means inside of the molecule between the atoms. So intermolecular. Yeah. So as a result, there will be dipoles attractions between the aldehyde molecules, making them have higher boiling points than corresponding alkane molecules, but lower boiling points than corresponding alcohol molecules. Right? So alcohol molecules are going to have hydrogen bonds between the hydroxyl groups of the hydrogen bonds between alcohol molecules due to that OH group that's present, the hydroxyl group, right? And hydrogen bonds, we know the strongest, in our course at least, the strongest form of intermolecular forces of attraction that a molecule can have. So dipole kind of lies in the middle of van der Waals, which are alkanes, alkenes, alkynes, all hydrocarbons have van der Waals forces of attraction, which are weaker. Relatives, all relative as well. So the lower aldehydes are soluble in water. Right. So why would that be the case? Soluble in both water and nonpolar solvents such as cyclohexane. The reason why the lower aldehydes are soluble in polar solvents such as water is due to the hydrogen bond between the oxygen of the carbonyl group and the hydrogen of the hydrogen molecule of the aldehyde and the hydrogen of water. The higher aldehydes are insoluble in water as the nonpolar carbon chain of the aldehyde molecule has greater influence. So what we've learned about this is that aldehydes, they have this kind of functional group, right? Group of atoms upon which the characteristic properties of homologous series, in this case the homologous series we're talking about is aldehyde, it depends. So first of all, aldehydes, they have a carbonyl group, yeah, and this carbonyl group is a pole. This carbonyl group is polar due to the electronegativity difference between the carbon and the oxygen. So carbon was 2.55, O was 3.44. So my electronegativity difference was 0.89. So 0.99 makes this a polar covalent bond intramolecular, so inside of the molecule, covalent bond. So this bond right here is polar covalent, yeah? This makes that the carbon and this, so carbon and oxygen, no, sorry. Carbon is, so oxygen is more electronegative and this is less electronegative. Yeah. So that's wrong. That's wrong. All right. So oxygen is more electronegative. Carbon is less electronegative. Yeah. So we know that, let's say aldehydes have higher aldehydes have dipole forces of attraction between the aldehyde molecules, which means they have higher boiling points than corresponding alkanes, but lower, so higher than corresponding alkanes because they have van der Waals forces of attraction, which are relatively they're much weaker, but which are relatively weaker in comparison. But they have lower boiling points when compared to alcohols, which have hydrogen bonds, intermolecular forces of attraction between the hydrogen molecules. Yeah. So because of this, we know that because of this carbonyl group, a beautiful thing happens. We know that the smaller aldehydes are going to be soluble in both polar solvents such as water and non-polar solvents such as cyclohexane, because the oxygen of the carbonyl group of the aldehyde forms hydrogen bonds with the hydrogen of the water molecule. But as the length of the non-polar carbon chain increases, its influence is greater. So therefore, it takes over from the polar carbonyl group. Yeah. So what we have to know is, so basically we need to know that methanol Methanol is a gas, but ethanol is a volatile liquid. What does volatile mean? Volatile means it has a low boiling point. So what we learned about aldehydes, they have a carbonyl group that's polar due to the electronegativity difference between the carbon and the oxygen, meaning that the oxygen is delta negative because of higher electronegativity value, and the carbon is delta positive because there's the lower electronegativity value. Then we also found out is because of this polar carbon group, the aldehydes have dipole-dipole force of attraction between the aldehyde molecules, meaning that's intermolecular forces of attraction, which makes its boiling points of higher than corresponding alkane molecules because they have van der Waals force of attraction between alkane molecules, but lower than corresponding alcohol molecules because they have hydrogen bonds between the alcohol molecules. However, we know that the smaller aldehydes are soluble in non-polar solvents and such as cyclohexane, polar solvents such as water. This is because the oxygen of the carbonyl group of the aldehyde forms a hydrogen bond with the hydrogen of the water. But as the length of the non-polar carbon chain increases, it takes over influence, right? It has a greater influence. Then we learned that methanol is a gas, but ethanol at room temperature, but ethanol is a volatile liquid at room temperature. So now we just have to draw a few. Okay, the first member of the. I enjoy chemistry, bro. I'll tell you. So that's that. Methanol, ethanol. S means 2 carbons. I think it's very good to see that the smallest member has 1 carbon. Ketone's smallest member is propanone because of 3 carbons, because you need the 2 carbons. Because the 1 carbon with the carbonyl group cannot be carbon 1. So here, like that, yeah? Then we have propanol. So I got bang, 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 double bond. Oh, wait. Alright. So this is propanol, yeah? We took the hydrogen like that. Beautiful, that's propanol. Alright. If I want to write the formula of this, I go H. It's always CHO. So CHO means it's an aldehyde. So it could be CH3CHO. Then it could be C2H5CHO. I just enjoy doing this, bro. Butanol. C. Man, we're gonna be successful. I'm telling you. Alright, because I've already done all of this. It's just revision, bro. It's just revision, which is the beautiful thing about this. Just make sure don't put hydrogens on this carbon because it's already double bonded to oxygen, to the carbonyl group there and the hydrogen. So yeah, so this is C3H7CHO. CHO is the key thing here. And then are they gonna structural isomers of what the hell is that molecule? Oh wait, let me just C4 C4H8O. Three isomers. So of course, first one is just gonna be butanol. So CC double bond O, single bond H, hydrogen, 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 hydrogen. Yeah. So it's C3H7CHO, which becomes that. Exactly, yeah. The next structural isomer that I'm thinking is possible is this. I don't know if this is even a molecule, but I think this is carbon 1. It's always carbon 1. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, and oxygen. Alright, so then I'm like, okay, 2 methyl propanol. And then the last one would be probably butanone. Yeah. So C. The one O can go on either this one or this one. It doesn't matter because we choose to put the carbon group in the carbon, which gives it the lowest position along the carbon chain. Oh, that's wrong. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So I use 2-methylpropanol, butanone, and yeah, done. All right. Oh, the names: butanone, 2-methylpropanol, and then just methanol. No, sorry, butanol. So benzaldehyde is an aromatic aldehyde that's found in almond oil of almond kernel. So benzaldehyde. It's an aromatic, which means contains a ring. An aromatic compound is a compound that contains a benzene ring in its structure, right? I had to think about that. Okay, wait. Aromatic aldehyde. Aldehyde. Yeah, so it's an aromatic aldehyde, yeah, meaning that it's just a benzene ring. And but the benzene ring, guys, please do not forget to put the little circle in, because that means it's not cyclohexane. Cyclohexane is C6H12. This is yeah. So then C double bond O single bond H. Now we have ketones, yeah. So kind of like the functional group of a ketone is like a carbonyl group, yeah. So we know that because ketones also have a carbonyl group as their functional group, they have a lot of similarities, yani, to the aldehyde molecules, and that's why the structural isomers were very similar as well. Now, because when we oxidize a primary alcohol to an aldehyde to a carboxylic acid, we also secondary alcohols get oxidized in the first stage to then excuse me, they get oxidized to ketones, right? So both are the first, yeah. So ketones also contain a carbonyl group, so they have many of the similar physical properties to the so the physical properties show a lot of similarities to aldehyde. The boiling points of ketones are higher than that of corresponding alkanes, but are lower than those of corresponding alcohols. The lower ketones are attractions, and the boiling points of ketones are higher than those of corresponding alkanes, as alkanes have van der Waals' intermolecular forces of attraction between the alkane molecules, but it's lower than corresponding alcohol molecules. The alcohol molecules have hydrogen bonding between the alkane molecules, so intermolecular force of attraction. So the lower ketones are soluble in water due to the carbonyl group of due to the oxidation of the carbonyl group of the ketone forming a hydrogen bond with the hydrogen of the water molecule. However, as the length of the nonpolar carbon chain increases, the nonpolar carbon chain takes over from the polar carbonyl group, and therefore the larger, higher up, like the larger ketones are not soluble in non-polar solvents such as no are not soluble in polar solvents such as water, but readily soluble in non-polar solvents such as cyclohexane. It's the same stuff. Solubility decreases like the yeah. So propanone is an excellent non-polar solvent itself. So propanone, it's a excellent. It's a non-polar solvent. Yeah. So the carbon of the functional group is never the first or last, and yeah, exactly. So again, just to recap this, ketones, right? They display many of the same physical properties as aldehydes because they too also have a carbonyl group as their functional group, the group of atoms upon which the characteristics of this homologous series is going to depend on. So, first and foremost, we talked about the boiling points of ketones, right, are going to be higher than corresponding alkane molecules. because the ketones are going to have dipole-dipole forces of attraction between the ketone molecules, intermolecular forces of attraction, due to the presence of this carbonyl group. But at the same time, the van der Waals forces of attraction to the alkene molecules are much weaker. But then the boiling points of ketones is going to be lower than the boiling points of alcohols, corresponding alcohols, as they have hydrogen bonds between the alcohol molecules, which are much stronger and require much more energy to break. Now, we know the solubility. So ketones, smaller ketones, are soluble in both polar solvents such as water, non-polar solvents such as cyclohexane. We know that as we know this is because the oxygen of the oxygen of the carbonyl group of the aldehyde forms a hydrogen bond with the hydrogen of the water molecule. But as the length of the non-polar carbon chain increases, solubility decreases as the non-polar carbon chain takes over from the polar carbonyl group. We know propanone itself is a great non-polar organic solvent. And yeah, and remember, the carbonyl group is never on carbon 1. So propanone is just this. Oh, sorry, shit. It has to be in the middle. So something like this. That's what propanone is gonna look like. Excuse me. That's what propanone. So propanone is also called acetone. It's a solvent. Remember, it's a non-polar solvent. It's a good non-polar solvent. So solvent in nail polish remover. So propanone is also known as acetone and is found in nail polish remover. Then we have butanol. So yeah. Can't wait to do the exam paper questions because we're speeding through this. Come on. Alright. Carboxylic acids, we know their functional group is C, double bond O, single bond O, single bond H. So they have both a carbonyl group and a hydroxyl group, which is pretty cool. Now, the boiling points of carboxylic acids are higher than corresponding aldehyde. Boiling points of carboxylic acid are considerably higher. So I want to see. Yeah. So the boiling points of carboxylic acids are considerably higher than corresponding alcohols, right? Due to the hydrogen bonding present between the molecules, so intermolecular force of attraction, caused by the polar OH group present in the functional group. The molecules also group together in twos. So molecules group together in twos, right? So this is called the dimers. So these carboxylic acid molecules are grouped together in twos and they're called dimers. Now, are held together by hydrogen bonds. As a result, more energy is needed to break these hydrogen bonds, hence the highest boiling point of all of the homologous series. So what we're saying is the boiling point of a carboxylic acid is considerably higher than, let's say, a corresponding alcohol molecule due to the hydrogen bonding present between the carboxylic acid molecules due to the presence of the OH group, the hydroxyl group. Now, we know that these carboxylic acids, they form groups of two called dimers, which are held together by hydrogen bonds. And that's why we say that carboxylic acids have the highest boiling points of all of the homologous series. Homologous series, remember, a group of compounds all contain the same functional group and successive members differ by CH2. So carboxylic acids are liquid at room temperature due to the hydrogen bonds holding the molecules together. The lower carboxylic acids are soluble in water due to the formation of hydrogen bonds with water. The oxygen of the carbonyl group of the acid forms an oxygen with hydrogen bond with the hydrogen in the water, and the hydrogen of the OH group forms the oxygen of the water. As the length of the carbon chain increases, solubility decreases. The higher members of acids are soluble in non-polar So what we need to know is that the rest of these, were gases at room temperature, except for like methanol. Methanol was a gas, but ethanol was a volatile liquid with a low boiling point. Now that means it didn't require much energy, right? To get it to a boil, right? It's a low boiling point. So carboxylic acids, we say that what is their solubility? Smaller carboxylic acids, they're soluble in nonpolar solvents such as cyclohexane, soluble in polar solvents such as water. But why are they soluble in water? Because this is cool. The hydrogen bond of the hydroxyl group of the carboxylic acid forms a hydrogen bond with the oxygen of the water, whereas the carbonyl group, where the oxygen of the carbonyl group of the acid forms a hydrogen bond with the hydrogen of the water. However, solubility decreases as the length of the nonpolar carbon chain increases, as it takes over from the polar OH group and carbonyl group. And that's why we say that the larger carboxylic acids, they're not soluble in polar solvents such as H2O, but they're readily soluble in nonpolar solvents such as cyclohexane. So these actually have a lot of uses. We have esters as well. So methanoic acid is known as formic acid. We looked about formaldehyde. We looked at how propanone was known as acetate, which is found in nail polish remover. The formic acid is found in sting ants and nettles. Sting ants and nettles. Now ethanoic acid is known as acetic acid. Now methanoic, ethanoic, propanoic, food preservative. So methanoic acid is called formic acid, which is found in sting ants and nettles. Methanoic acid is called acetic acid. No, ethanoic acid is called acetic acid, and propanoic acid is used as I think benzoic and propanoic are both food preservative. Methanoic acid usually act as aldehyde, so structure contains an aldehyde functional group. Now, methanoic acid found in nettles, ethanoic acid used in the manufacture of cellulose acetate. So ethanoic acid is known as acetate, also known acetic acid, used in the manufacture of cellulose acetate. Acetate though was propanone. Propanone was acetate. Acetone. Oh shit. That's acetone. This is acetic. Oh my god, bro. What the hell? So acetone found in removes propanone. But then ethanoic acid is acetic acid. That's acetone. This is acetic acid, which is used to form cellulose acetate. Used in manufacture of cellulose acetate, which is used in varnishes and vinegar. Propanoic acid and benzoic acid are used as food preservatives. So methanoic acid is formic acid found in sting ants and nettles. So the way it's going to look is C double bond O, single bond O, single bond H, methanoic acid. Ethanoic acid, ethanoic acid known as acetic acid, used in the manufacture of cellulose acetate, which is found in varnishes and vinegar, and then which found in what varnishes? What type of varnishes? Yeah, and then we have COOH, CH3COOH. That's a familiar site because that's in one of our titrations that we looked at, the dilute vinegar, and that's so that's in one of our titrations. Then we have CCC. This is propanoic acid and benzoic acid are used as what? They are used as food preservatives. So It's good to just practice drawing these molecules, I swear, bro. Remember, show all bonds, all atoms, all of the time, so that's very useful. CH3, sorry, C3H7COOH. Yeah. So now we have esters. So they have functional group of the esters is circled in the diagram, so it's probably that little thing. What is that? Functional group. So esters are compounds formed when the hydrogen of the functional group of a carbon. So esters are formed when the hydrogen of the carboxylic acid is replaced with the ethyl radical of an alcohol, with the alkyl radical of alcohol. So when the hydrogen esters are compounds that are formed when the hydrogen of the functional group of the carboxylic acid is replaced with the alkyl radical of an alcohol. So the hydrogen of the functional group of the carboxylic acid is replaced with the alkyl radical of an alcohol. They are formed by a reversible reaction between carboxylic acid and an alcohol to give an ester and H2O. A condensation reaction occurs when two different molecules combine to produce a more complex molecule, with H2O as being produced as a product molecule. Wait. A condensation reaction occurs when two different molecules combine to form a more complex molecule with the production of a smaller molecule. When two different molecules, so condensation reaction is two different molecules combine to form So when two different molecules combine to produce a more complex molecule with the production of a smaller molecule such as H2O. Think about it. H2O is produced, ester, like an alcohol and a carboxylic acid are coming together because the hydrogen of the functional group of the carboxylic acid is being replaced with the alkyl radical of an alcohol. So that is pretty cool. Condensation reaction is when two different molecules combine together to produce a more complex molecule with the production of a smaller molecule such as H2O. When two different molecules combine to form more complex, they have relatively low boiling points due to the dipole-dipole attractions between the molecules. Lower esters are soluble in water as the oxygen of the carbonyl group. Yeah, they have a carbon. It's like C double bond O, so R. Yeah, so it's like that. Is that it? No, single bond O, single bond R. Yeah, that's it. So we know that they have relatively low boiling points due to the dipole-dipole forces of attraction between the ester molecules. And we know that the lower esters are soluble, smaller esters are soluble in both non-polar and polar, so polar solvents such as water, non-polar solvents such as cyclohexane, due to the oxygen of the carbonyl group of the ester forming a hydrogen bond with the hydrogen of the water molecule. But as the length of the non-polar carbon chain increases, solubility in water decreases, and therefore more larger esters are soluble in non-polar solvents such as cyclohexane. Name esters more. All the reactions are in this. Beautiful. Alright, now it says name this. This will probably be CH3 COO. This is going to be methyl ethanoate. This is going to be methyl methanoate. This is going to be ethyl ethanoate. Now write the formula of this. So butyl ethanoate, meaning it's going to be C2H5. No. Yeah. C2H5 COOC C and then butyl. Then it says propylmethanoate, so CH3. No, that's not methyl methanoate. You know what I'd actually tell you to do? If you're struggling with this, yeah, just draw out the molecule, bro. There's no point taking shortcuts. There's no point taking shortcuts and getting it wrong. So C, double bond O, single bond O, C, H3. So now you can see it's just methyl. And I don't want to waste paper, so I'll just so. And this one is like C, H, double bond O, single bond C, H. So it's I'd always just write it out, you know. Butyl ethanoate. Oh. Propylmethanoate. Okay. Oh, sorry. C3 367. Yeah. Then it says propanoid. So propanoid goes here. Actually, you could probably start with the ethyl group. So C, the one C. Yeah, so the end of it's going to be C2H5 COO. And it's ethyl, so it's going to be CH3. That works. And ethyl ethanoate. So ethyl is C2H5 O C. But it's ethyl. So CH3. Oh, so that one's ethyl ethanoate. This is ethyl pro. Ethyl propanoate. Bro, this is difficult, man. So Ethyl, methyl, chethyl is all on the bottom. And the ennoate part is the bro. This would be propyl methanoate. This would be ethyl ethanoate. So polyester is a term that you should be familiar with. Is given to a synthetic fiber such as tyrolene, usual tristearate. So perfumes. So the same way the way propanone is used as a non-polar solvent, ethyl ethanoate is used as a non-polar solvent. Right? So you go primary alcohol gets oxidized to an aldehyde, gets oxidized to a carboxylic acid. Two different molecules combine together for a more complex molecule with the production of a small molecule such as so secondary alcohol is straight to ketone, and along the whole way it's Cr2O7 2 minus. So it's like Na2 this is our oxidation agent. This stuff is getting reduced. So Cr plus 6 is getting reduced to Cr plus 3 every time. Yeah. So now we have some beautiful diagnostic tests, because why not? I know. So diagnostic tests. I know it's going to be acidified KMNO4 is one of them. Tollens reagents are one of them, and then Benedict solution is the third one, right? I hate this. But I need to push through, bro. I've already procrastinated too much. I made too many mistakes. Kind of when push comes to shove, bro, you just have to do it. Alright. Permanganate. So ethanol with acidified potassium permanganate. So, so place a few centimeters cubed of ethanol in a test tube, along with a few centimeter cubes of ethanol into a test tube, along with some acidified potassium manganate 7. Right? Acidified potassium manganate 7. Heat gently in a water bath for a few minutes. Result is the purple color of the manganate 7 goes colorless, as the ethanol is the reducing agent and reduces Mn plus 7 to Mn plus 2. Because if you think about the ethanol itself, it's getting oxidized, right? So then it's reducing. So we're going to place a few centimeters cubed of ethanol into a test tube with some acidified potassium manganate 7. We're then going to place the test tubes in a water bath. Heat gently in a water bath for a few minutes. The purple potassium manganate 7 will turn colorless, as ethanol acts as the reducing agent and reduces Mn plus 7 to Mn plus 2. So first of all, we have ethanol solution. place So essentially, we're going to add a few centimeter cubed of ethanol to a test tube containing acidified potassium manganate 7 solution. Heat gently in a water bath for a few minutes. For a few minutes. So we're going to add a few centimeters cubed of ethanol to a test tube. We're going to place a few centimeters cubed of ethanol. Place a few centimeters cubed of ethanol with some acidified potassium manganate 7 solution. Heat gently in a water bath for a few minutes. The purple potassium manganate 7 goes from purple to colorless as ethanol, the reducing agent, reduced Mn plus 7 to Mn plus 2. So we have ethanol, CH3, CHO, plus Mn plus, plus Mn plus 7 is going to give me CH3 COOH plus Mn plus 2. So place a few centimeters cubed of ethanol into a test tube and add some acidified potassium manganate 7. Heat gently in a water bath for a few minutes. The potassium manganate 7 will turn from purple to colorless as ethanol, the reducing agent, has reduced Mn plus 7 to Mn plus 2. So our equation is CH3CHO, which is ethanol, plus the Mn plus 7 goes to Mn plus 2 plus ethanoic acid. Yeah. Be acidified. Full oxidation of ethanol to ethanoic acid. I mean, that's probably it, to ensure the full oxidation of ethanol to ethanoic acid. Now we have ethanol and it's like added Felling's A plus B solution to a test tube, add a few centimeters cubed of ethanol. If it goes from blue to red precipitate or some shit like that, yeah. Place a few centimeters cubed of ethanol into a test tube. Add equal volumes of Felling's A plus B solution, blue in color due to the presence of copper 2. Heat gently and shake to mix. The blue color of the Felling solution changes to a red precipitate. Of the manganate 7 goes right. Changes the blue color of the change to red precipitate. This is due to ethanol acting as a reducing agent, which reduces Cu2 plus to Cu plus, which is a red precipitate. So we're going to place a few centimeters cubed of ethanol in a test tube, add equal volumes of Felling's A plus B solution to the test tube, which is blue in color due to the presence of carbon 2. Heat gently and shake to mix. The blue color of the Felling solution will turn to a red precipitate as the ethanol, the reducing agent, has reduced Cu2 plus to Cu plus, which is a red precipitate. So CH3 CHO plus Cu2 plus is going to give me CH3 COOH plus Cu plus. Yeah, okay, that's easy. And last but not least, yeah, so this here, this is blue, you know, copper 2 sulfate solution. This is a red precipitate. And then last but not least, we have the ethanol and reagent, or yani silver mirror, whatever you want to call it. Tollens reagent, silver mirror, ammonical silver. So tollens reagent, silver mirror. This is actually ammonical silver nitrate solution. Ammonical silver nitrate solution. Ammonical silver nitrate solution. I know, I swear, bro. So ethanol and Tollens reagent. So it's ammonical silver nitrate solution. It's also known as the silver mirror test. So place a few centimeters cubed of ethanol into a test tube. Add a small amount. Okay, place a few centimeters cubed of silver nitrate into a test tube. Add a small amount of sodium hydroxide. Place a few drops of ammonia aqueous until the silver oxide precipitate disappears. And then add a few drops of ethanol and warm gently. Now, result is a deposit of metallic silver seen on the inside of the test tube. Place a few centimeters cubed of silver nitrate in a test tube. Add a small amount of sodium hydroxide. Add a few drops of ammonia to the test tube until the silver nitrate precipitate dissolves. And then add a few drops of ethanol and heat gently. And a deposit of metallic silver is seen on the inside of the test tube. This is due to the silver Tollens reagent. This is due to the ammonical silver nitrate solution. So this is due to the silver in the Tollens reagent, which has an oxidation number being of Ag plus 1 being reduced to Ag0. So CH3CHO plus Ag plus is going to give us CH3COOH plus Ag. So three tests. First of all, we had ethanol and acidified potassium permanganate solution. So place a few centimeters cubed of ethanol into a test tube, and add some acidified potassium manganate 7 to the test tube as well. Yeah. We're going to heat gently by placing in a water bath for a few minutes. And the manganate 7 turned from purple to colorless as the reducing agent ethanol reduced the Mn plus 7 to Mn plus 2. So we got CH3CHO Mn plus 7. Let's give CH3COH was Mn plus 2 or 2 plus. Then we had the Felling solution and ethanol. So we're going to add place a few centimeters cubed of ethanol into a test tube. Place equal volumes of Felling's A plus B solution into the test tube, and this Felling solution is blue in color due to the presence of copper 2. Then we're going to heat gently and shake the mix. Then we know that the Felling solution is going to turn from blue to red precipitate. And this is because the ethanol, which is the reducing agent, has reduced the copper 2 plus to copper plus, which is a red precipitate. So CH3CHO Cu2 plus is going to give CH3COH plus Cu plus, which is a red precipitate. Last but not least, we have ethanol and the Tollens reagent, or ammonical silver nitrate solution. So essentially, we're going to place a few centimeters cubed of silver nitrate into a test tube, add a small amount of sodium hydroxide, place a few drops of ammonia into the test tube until the silver nitrate precipitate dissolves. Then place a few centimeters of ethanol into the test tube and heat gently. And warm gently. We know that a deposit of metallic silver will be seen on the inside of the test tube. A deposit of metallic silver will be seen on the inside of the test tube. Why? This is because the Ag plus in the silver nitrate was reduced by ethanol to Ag0, which is silver atoms, right? So remember, warm gently as well. So preparation of a ketone. Remember, reduction in these redox reactions is always going to be done with a nickel catalyst as our condition, but our reagent will always be H2. So we looked at Tollens reagent, we looked at Felling's A plus B solution, and we looked at acidified potassium permanganate solution as well. Now, so the deposit of metallic silver will be seen along the inside of the test tube. This is because the silver plus one in the silver nitrate solution was reduced to silver zero, or silver atoms, by the ethanol, which acts as the reducing agent. So this is one of the hardest chapters, I would say. Like, it's kind of heavy. It's really important, though. It's really important. So ethanoic acid, first of all, the diagnostic test. So first of all, number one is going to be ethanoic acid with sodium carbonate, I think. Yeah, sodium carbonate, which is also known as a diagnostic test. So ethanoic acid with yani with sodium carbonate. So we have CH3COOH plus sodium carbonate. So if we know from the acid chapter, carbonate is going to give us a metal plus a CO2 plus a H2O. So we know CO2 plus H2O, but the metal is going to be CH3COONA. So within two times that, there's two NAs. There's one carbon. So how many? First of all, how many carbons are there? There's two. There's three. There's four. So there's two. There's three. There's four. Fine. Oxygens. There is yani 1, 2, 3, 4, 4, 4, 7, 7. 4, 5, 6, 7. Okay. And then hydrogen. There's two hydrogens here. Sorry, no. 6, 7, 8 hydrogens here. 6 hydrogens here. 6, 8. Balance. خلاص done. So a spatula load of sodium carbonate was added into a test tube. Spatula load. Then a few centimeters of ethanoic acid was added. A result was effervescence was observed as carbon dioxide gas was given off. Yeah. This carbon dioxide quenched a lighted taper held at the mouth of the test tube. So essentially, a spatula load of sodium carbonate was added into a test tube. A few drops of ethanoic acid was placed into the test tube as well, right? So the observation was effervescence as carbon dioxide gas was given off, and we know that the carbon dioxide gas would quench a lighted taper when brought to the mouth of the test tube as well. So then we give this whole so this is called sodium ethanoate. Yeah, sodium. Because the hydrogen of the functional group of the carboxylic acid is replaced by a metal ion as opposed to an alkyl radical of an alcohol, as we see in esters. Then we have a few questions, right? So reaction reaction of ethanoic acid with sodium carbonate was that with magnesium. Reaction of ethanoic acid with magnesium metal. So CH3COOH plus a metal is going to give us salt plus H2O. Salt plus H2. Plus, let's see. I think my chemistry is good. I still remember these things. Thank God. So a test tube was quarter filled with ethanoic acid, and then around 3 centimeters of magnesium ribbon was then added. The result is the magnesium ribbon disappeared and hydrogen gas was given off. So this is magnesium ethanoid. Magnesium. So a test tube was quarter filled with ethanoic acid, and about 3 centimeters of magnesium ribbon was added to the test tube. The result was the magnesium disappeared, hydrogen gas was given off. That's it. And then the other one, sodium carbonate. So essentially what happened was we had a spatula load of sodium carbonate to our test tube. Then we placed a few drops of ethanoic acid into the test tube. And what we see is effervescence as hydrogen gas is being given. Effervescence as carbon dioxide is being given off. If we bring a lighter taper near the mouth of the test tube, the flame will become quenched because it needs oxygen to burn, right? Combustion, remember? Any organic molecule plus O2 is equal to CO2 plus H2O. So yeah. So yeah, exactly. Yeah. And last but not least, so that was easy. Add basically quarter fill the ethanoic few centimeters cube of the ethanoic acid was that few centimeters cube. Then with magnesium metal, it was, quarter fill a test tube with ethanoic acid, then add around 3 centimeters of magnesium ribbon to the test tube, and then magnesium disappears. H2 is given off, so you'll see some effervescence probably as well. Then we have so this is esterification. So you'll see like the hydrogen in the hydrogen of the functional group of the carboxylic acid is replaced with the alkyl radical of an alcohol. Condensation reaction, esterification reaction, condensation reaction, when two different molecules combine together to form a more complex molecule with the production of a smaller molecule such as H2O. H2O. So essentially, if let's say I'm using ethanol plus ethanoic acid. I'll show you exactly what it looked like. So ethanol, we know C ethanoic acid. That's exactly what it's going to look like. So that's ethyl ethanoate, that's ethanol, that's ethanoic acid, and that's H2O. So we see that this reaction is reversible, so it's affected by changes in concentration, not pressure, concentration, and changes in temperature as well, because exothermic, endothermic. It's a reaction, so endothermic, so temperature rise will favor the endothermic as the use of the energy that's absorbed by the reaction, and exothermic will favor the reaction that's like losing heat, right? So as to regain the energy that was lost to the surroundings. And concentration, well, so higher concentration, if let's say we have a higher concentration, it'll favor the side that uses up the substance that was added, and then lower concentration will favor the side that makes that substance that was removed. So yeah, so sulfuric acid, the purpose of pressure, why? Because it's not a fully gaseous system, right? This is a liquid, this is a liquid, this is a liquid, there's no gas. Okay, So the purpose of concentrated sulfuric acid. Under reflux. So this occurs under reflux. Under reflux. It's like where it's like condenses, but then it condenses back into the boiling thing. Yeah, we'll look at that. We'll look at that in the next chapters. So under reflux, the reason why we added sulfuric acid acts as a dehydrating agent. It's a dehydrating agent causing water concentration to decrease, of course, if it's a dehydrating agent. If the water decrease favors forward reaction, so equilibrium shifts to the right, rate of the forward reaction increases as to produce more ester, to produce more of ester, and then catalyst. So the sulfuric acid in this reaction under reflux, in this esterification reaction, where we're basically taking two different molecules combined together to form a more complex molecule. We get a smaller molecule with the production of a small molecule such as H2O. It acts as a dehydrating agent, reducing the concentration of H2O. Then the side is going to be favored, the side that produces that to replace the H2O that was removed. That's going to be the forward reaction, more ester is going to produce. It also acts as a catalyst as well. I'm just going to do some of them because, of course, I can't do every single one because I need to do the next chapters as well. And I kind of forgot them. Can't lie. They were a bit annoying chapters. So, functional group. Okay. Functional group of an aldehyde is. Sorry, like that. Well, I should draw it properly. C, double bond O, single bond H. Carboxylic acids is going to be C, double bond O, single bond O, single bond H. Name of molecule. So it's an aldehyde. So it's. Just draw it out. First of all, just draw it out. It actually helps so much. So draw it out. So CH3, CHBr, and I'm like C. So it's definitely propanol, 2-bromo propanol. What is an ester? An ester is a carboxylic acid where the hydrogen of the functional group of the carboxylic acid has been replaced with the alkyl radical of an alcohol. Draw the structural formula for this ester. This is going to be methyl methanoid, but yeah, methyl methanoid. Give two functions of using concentrated. So concentrated sulfuric acid acts as a dehydrating agent, therefore reducing the concentration of H2O. Therefore, equilibrium shifts to the left. Therefore, as to replace the H2O that was removed, and therefore more esters produced. It also acts as a catalyst in the reaction as well. Which of the following molecules has a higher boiling point? CH3CHO or C? So definitely, ethanoic acid is going to have a higher boiling point than ethanol, as ethanoic acid is going to have hydrogen bond intermolecular forces of attraction between the ethanoic acid molecules, which is much stronger than the weaker dipole-dipole forces of attraction found between the ethanol molecules, and therefore the boiling therefore so it requires more energy to break the hydrogen bonds between the ethanoic acid between the acid molecules as opposed to the aldehyde molecules, and therefore requires more energy. Now, how many tetrahedral carbons would you find in ethyl methanoate? Ethyl methanoate. So let's do methanoate. So C. Two tetrahedral C. Just two. What is meant by condensation reaction? Condensation reactions where two different molecules combine together to form a more complex molecule with the production of a smaller molecule such as H2O. How many isomers are there? So isomers are molecules with the same molecular formula but different structural formula. So isomers are there. There's three isomers. I'll just name them. So we have butanol, 2-methylpropanol, and butanone. Draw and name the final product produced by the reduction of butanone. So the reagent was H2, and it's gonna be butan 2-ol. Now classify the alcohols. This is a secondary alcohol. This is a primary alcohol, propane 2-ol, because there's two carbon atoms bonded to the carbon atom which is directly bonded to the OH group. No, two carbon atoms directly bonded to the carbon which has the OH group attached. Butane 1-ol is a primary alcohol because it only has one carbon atom directly bonded to the carbon which is bonded to the OH group. I mean, it says which reagent could the student could have used. I mean, they could have used a monocle silver nitrate solution with sodium hydroxide and ammonia. They could have used Felling's A plus B solution. They could have used potassium permanganate, acidified potassium permanganate 7 solution. State the color change for acidified potassium permanganate solution would be purple to colorless. For the Tollens reagent, it would be uh, colorless to silver deposit, and then it would be blue to red precipitate for the Felling solution. So I mean, like Mn plus 5 electrons, Mn plus 2, that's the same. A few drops of oxidizing reagent were added to 0.5 centimeter cubed of ethanol in a test tube. What was observed when warm dilute? It went from purple to colorless. Felling's reagent preheated. It went from blue to red precipitate. Identify the organic product of oxidation of ethanol using these reagents. Ethanoic acid. Felling's reagent is quite difficult to reduce. Is ethanol very easy or difficult to oxidize? Ethanol is very easy to oxidize. Right at Hallen's hydrogen, so Cu2 plus. So Cu2 plus, they gain an electron to form Cu plus. Ethanol is completely miscible. Describe the polarity across the carbonyl group in ethanol. So we know that the carbonyl group in ethanol it's a polar due to the electronegativity difference being 0.89. We know that the carbon is delta positive as its electronegativity is less, value is less than the oxygen, which is delta negative, which has a higher electronegativity. Refer to polarity across a carbonyl group to explain why ethanol is very soluble in water. Because Due to the electronegativity difference, it's a polar. So the oxygen of the carbonyl group of the alcohol of the aldehyde forms a hydrogen bond with the hydrogen of the water molecule, and therefore it makes ethanol very soluble in water, and also the length of the nonpolar chain is small enough to the point where it doesn't interfere with the polar carbonyl group as well. Now it says, study this reaction scheme below and answer the questions that follow. Give a major use for Z, carboxylic acid. Oh, ethanoic acid is called acetic acid, used in found in varnishes and يعني vinegar as well. And then aldehyde Y, which is well, it says draw the structure. I remember methanoic acid is formic acid. I know the propanone is called acetone, which is found in the right? And methanol is also known as formaldehyde. Now draw the structure of the aldehyde. So two carbons, right? So C, double bond O, single bond H, 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 H. Draw the structural formula of the ester formed when from compounds X and Z. So planar geometry, this carbon here. How could aldehyde Y be reduced to alcohol X? Reagent is H2, condition, nickel catalyst. Bro. Reflux, we don't know, but give two reasons. So, okay. So it says the chart compares the boiling points of alkanes and primary alcohols. So, alkane, sorry, alkane and primary alcohols. Give two reasons why containing 1 to 4 carbons. It says give two reasons why each of these three alcohols has a higher boiling point than the corresponding point. So first of all, the alcohols are going to have dipole forces of attraction between the but the alcohols. So sorry. Alcohols are going to have hydrogen bonds between the alcohol molecules, which require a much more energy to break than the weaker van der Waals forces of attraction found between alkane molecules. We know that the boiling points of the alkanes increase as the length of the nonpolar carbon chain increases. This is because therefore there's more van der Waals forces between the alkane molecules, and therefore requires more energy to break these van der Waals forces of attraction between the butane molecules, and therefore that's why the heat different the temperature, the energy that's required, it reduces the difference reduces. Solubilities of methane and methanol, butane and butanol. I mean, methane Alkanes are not soluble in polar solvents such as water, as they do not form hydrogen bonds with water, but they're readily soluble in nonpolar solvents such as cyclohexane. Methanol, smaller alcohols are soluble in nonpolar solvents and polar solvents such as water, and nonpolar solvents as such as cyclohexane. This is because the hydroxyl group forms hydrogen bonds with the water molecules. However, as the length of the nonpolar carbon chain increases, solubility decreases in water, and that's why the larger alcohols are not soluble. So methanol, so methane would be not soluble. Methanol would be soluble. Butane, I don't know. I think butane would be soluble. Is butane soluble? No, no, it's not. Yeah, because it's an alkane. Oh, I'm such a stupid. Oh my god. Okay. Okay. This chapter is revised and done and dusted, and everything is all good and happy and lovely. Don't ask why I said that, but how long have we been doing this for? How long have I been doing this for? 121. What was the name of the chapter? Yeah, it was the periodical substitution, isn't it? Mashallah. Here it is. Alright, here is the stuff that we need. We're actually pushing. We're plowing through. We're plowing through. Are we though? Are we like? I'm trying. Okay. I think you have plenty of time to get all of this stuff done. I'm not doing the options. Screw the options. They can keep the options to themselves, bro. I just need the H1. I don't care about getting 100%. Just give me the H1. I'm happy. I'm happy out. I'm happy out, lads. So now we're going to look at the mechanisms. Yeah. So free radical substitution. What does that even mean? Like, what does free radical substitution? What the hell is even that? Like that's the thing I'm trying to say here. Is what the hell is even that? Like what the I didn't. Well, I didn't have time to do it, but I can't lie. I already studied enough of the other stuff, bro. So let's just go to free radical substitution. What is the meaning of free radical substitution? Occurs when an atom or a group of atoms is replaced by another atom or group of atoms, and there are two products. Uh, when an atom or group of atoms So when an atom or group of atoms is replaced by another atom or group of atoms, yeah. So we have one free radical substitution reaction we need to know, which is the we usually use ethane or methane with Cl2, UV light 200 degrees Celsius. No, UV lights are conditioned, and then we get the chloroalkane and the hydrogen chloride, right? Okay. Initiation. So how does initiation look like? So initiation. So a free radical is a pair or group is an atom or a group of atoms. So a free radical is an atom. A free radical is an atom or group of atoms with an unpaired electron. Free radical substitution reaction occurs when an atom or group of atoms is replaced by another atom or group of atoms, and there's two product molecules. So first stage of this is initiation. So let's say I have my two Cls, right? So Cls, right? I go UV light and a Cl. This, my friends, is a unpaired electron. That's an unpaired electron. So this is still an atom with an unpaired. And this is called homolytic fission. So homo means the same. So splitting of a chlorine molecule into two identical atoms. So essentially, we have Cl. The electrons are being shared, and then we separate it. So homolytic fission is when the chlorine molecule is separated into two chlorine atoms. The splitting is the splitting fission. It's the splitting of chlorine into two identical chlorine atoms. This is initiation, so it's an unpaired electron, still an atom with an unpaired electron. Homolytic fission is the splitting of chlorine molecule into two identical atoms. Then we have propagation. So propagation. Propagation. So Cl plus Cl, but let's say I'm going with methane. It's going to give me CH4. Sorry, it's going to give me CH3 plus HCl, then CH3. So this is like chain. So this is known as a methyl free radical. And this is called a chain reaction. So what we call a chain reaction, yani, okay? Alright, so essentially the way propagation works, we're going to take one of these Cls and I'm going to react it with whatever I have. So let's say I have methane. It gives me a methyl radical and hydrogen chloride. I then take my methyl radical and I react it with Cl2, so I get a chloromethyl. I get one chloromethane and I get Cl. It's a chain reaction, propagation, and then termination. This shit's easy, bro. So Cl radical plus Cl radical gives us Cl2. Cl radical plus CH3 radical gives So initiation, yeah, is homolytic fission. So the molecule of chlorine is split into two identical atoms, Cl, Cl. They still have uh, still atoms with still an atom with an unpaired electron. We see the unpaired electrons. Then we have the propagation, which is our chain reaction. So let's say I have the chlorine radical will react with whatever, so ethane, methane, whatever it may be, and it's going to give me, let's say I take methane, right? It's going to give me CH3Cl. It's going to give me CH3Cl plus HCl, and the CH3 radical, so the methyl radical is then going to react with a chlorine to give me chloromethane and a methyl radical, and then it just repeats, and then termination, chlorine radical gives me chlorine molecule, and then chlorine radical and methyl radical gives me chloromethane, and methyl radical gives me ethane. And remember, just again, a free radical is an atom or group of atoms with an unpaired electron, and a free radical substitution reaction is one where an atom or group of atoms is replaced by another atom or group of atoms, and there's two product molecules. Okay. Evidence. So react. See, I just still remember it. Like, it's not, it hasn't gone from my brain. It isn't completely kaput, like. Thank God. Thank God. Now we're looking at. Oh, clove oil, soap, benzoic acid crystals, recrystallization. So now we have ionic addition reactions. Whew. When two when two substances react together to form one main. So free radical substitution reaction occurs when an atom or group of atoms is replaced by another atom or group of atoms, and there's two product molecules. Ionic addition reactions occur when two substances react together and form one main product. So we have four stages. Stage A is the first one. So Cl2, UV light. There's lots of that. There's lots of HCl being produced. There's lots of. Sorry, one last thing I need to do. Sorry, my keyboard's kind of getting in the way there a little bit. So sorry, before we do that, so if we have UV light for free radical substitution versus no UV light, will have HCl, we have HCl, we have CH3Cl, and we have trace amounts of lots. But here we'll just have Cl2 and CH4, for example. No UV light. Otherwise, we'll get hydrogen chloride. We'll get the chloromethane, and we'll get trace amounts of ethane as well. Yeah. So now we're looking at stage A. So ionic addition reaction where two substances react together to produce one main product. So first of all, we have a thing called the polarization of bromine molecule. Like this is bromine. It could be hydrogen. It could be water. It could be hydrogen chloride. It could be chlorine, bromine, hydrogen, whatever you want to say. So polarization of bromine molecule is, let's say, because free radical substitution looks like this, right? No, sorry, this is ionic addition, sorry, yeah. Right. This is the area of negative charge. So area of negative. This is the area this is the area of negative charge, and then I have basically a bromine molecule, right? So polarization of bromine molecule. So I have Br-Br. Now this is delta, because this is delta positive, and this is delta negative, yeah. So this over here, we have 4 shared electrons. So basically what happened here was this bromine molecule moved from here to here. It got pushed because of the area of negative charge. 4 shared electrons here. So polarization. So now it has poles. So polarization of bromine molecule. Polarization of bromine molecule caused by electrons in double bond. Yeah. So essentially, we have our ethane molecule. The double bond is the area of negative charge. We have 4 shared electrons. Then we have bromine. The bromine that's near the ethane, near the negative charge, is delta positive, but the delta negative got pushed too far, right? Because the polarization of the bromine molecule occurred is due to the electrons in the double bond. Now, this was just polarization of bromine, so not really too much of a big deal. Then we have stage B. It's called heterolytic. So we had homolytic fission, where the molecule of chlorine split into 2 identical atoms. Here, heterolytic fission is heterolytic fission states that bromine molecule into 2 different ions, because hetero splits into 2 different ions. So now everything's the same, but the delta positive now becomes bromine plus, and the delta negative now becomes bromine minus. Then we have stage C. My anxiety is like freaking bad, bro. So we have basically a positively charged carbon. This is known as a carbonium ion. Formation of carbonium ion. It's a temporary intermediate species. Intermediate temporary species. So it's an intermediate. Twelve, 13, 14, 15. Yes, 2 weeks. Okay, so this is a positive charged carbon. Stage D is just you get our product. So sometimes you get to XAG. You don't see really a drink. Okay, so stage A, what happens in stage A? It's a polarization of the bromine molecule, so it gains poles. So in the ethane molecule, the double bond is the area of negative charge because there's four paired electrons, right? So there's four electrons in the double bond, so four shared electrons. Now the delta bromine molecule is polarized, so delta positive bromine is near the ethane molecule, but delta negative is far away. It got pushed away, right? So the polarization of the bromine molecule occurred due to the electrons in the double bond. Stage 2 was the heterolytic fission. So the bromine molecule splits into two different ions. We have a positive bromine ion and negative bromine ion. Of course, we know that the positive bromine ion is going to be near to the ethane and the negative bromine ion is going to be repelled away. Then stage C is the formation of the carbonium ion, which is an intermediate temporary species that forms, which is like it's like a C HHBr C plus HH, and we get the bromine minus, and then stage D is just the formation of the carbon, so 1,2-dibromo ethane, right? So ionic addition reactions are reactions yani where so ionic addition reactions, a reaction where two substances react with each other to form one main product molecule. Now we need to do evidence. I'll be back from the toilet, yeah, and we'll do evidence as well, yeah? Come on. Bro, I'm back. Oh, I forgot to unmute my mic. A bromine molecule, bromine molecule splits into two different ions. So let's just draw this. We're fast with it, bro. See that? And then stage C, formation of carbonium ion. This is like H, C, H, Br, C, H, H plus. This is Br minus, yeah? Br minus. It's an intermediate temporary species, يعني, yeah? And stage D is formation of product. So I mean, yeah, I guess so. So H, C, C, H, 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 Br, Br, 1,2 dibromo. I mean, evidence, yani, trace amounts of. So if I come here, let me just draw out my ion. So Na plus OH minus Cl minus H plus amounts of proves and I'll just do one polymerization question. I think I'll call it, bro, because I need to move on. I need to move. So H. Yeah. Sorry. Yeah, bro. You know I get stressed out like shits, bro. I know it's one bromo ethanol. The next one is like bro, this is like speed run. This is literally speed running the course, bro. BR, and then it's like يعني Cia, yeah. So 1 bromo, 2 chloro, ethane, yeah, and then ethanol, bro. To make sure. Okay, polymerization. So use of chloroalkanes is chloroalkanes are used to remove oil-based stains from clothes in the dry cleaning industry. They're used as propellants in aerosols. They're used as coolants in air conditionings. Mechanism which involves chlorine and ethene. It's ionic addition reaction. Ultraviolet light in the reaction between chlorine and methane. It allows for the homolytic fission of the chlorine molecule to form two identical atoms. Name and account for the two main products between chlorine and methane. Methane is chloromethane and hydrogen chloride. Trace for ethane proves the existence of methyl radicals. Yeah, no, like I know this shit, bro. I've been there, done that, tasted that, bro. You see me, man? I've been there. I've seen it. I've seen that life, bro. Alright, let's go steam distillation of clove oil. I don't even care, bro. I'm on a low, man. I don't even care anymore, man. I think I'm gonna have to search in my drawer, one of these drawers here, somewhere. I hope I have it. Oh man, we're gonna have to speedrun physics. We're gonna have to speedrun everything, bro. At this point, don't ever let fear put you down, bro. You're well capable of achieving your dreams, bro. Even when the odds are stacked up against you, everything's against you. And even when everyone else seems like they're doing so amazing, it's just really a deception because you focus on yourself And you do the best that you can possibly do, given the circumstances. Yeah, myself. To be honest with you, bro, I've not been the greatest. Oh, it's all here. All the canvas all here. So I need organic. Organic, yeah, I need organic. 6. Organic. Yeah, I need base hydrolysis. I don't need boards, modeling, because I will be needing this. I will be needing this. Cause yeah, cause so go back. I don't even have the timer. Where's the timer gone? Oh, I just ran out. Oh, why am I accompanying this up? You can see my workspace kind of messy out, like. Yeah, we need to go. We need to go. We need to go because we ain't got time. Yeah. Okay. Right. So first of all, when we talk about benzene, so we're going to be talking about organic 6, and we're going to be talking more specifically about the benzene molecule. It's such a beautiful molecule. Yeah. So we have already learned that atomic compounds contain a ring in their structure. The ring that we need to study more detail is benzene ring. Benzene is formed as C6H6, so we can see from this formula that the benzene highly unsaturated. So benzene has 6 carbon atoms. 6 carbon atoms arranged in a ring structure. Each carbon atom has 4 electrons in its outermost shell, because if we look here, the valency of carbon is 4, because it's 1, 2, 3, 4, 3, 2, 1, 0. So 4, which means it tells us the number of chemical bonds an atom of an element can form. And then 3 of these electrons form sigma bonds. Sigma bonds is the end-on overlapping of atomic orbitals occur between an S and a P, a P and a P, and a P and an S. An S and S, sorry. Yeah. 2 sigma bonds are formed between each carbon atom and the the 2 carbon atoms on either side of it. Third sigma bond is formed between the carbon and the hydrogen atom. So exactly, yeah. So each carbon atom, so a benzene ring has 6 carbon atoms. Each carbon atom has 4 electrons in its outermost shell, right? Two of those electrons in that outermost shell form sigma bonds. Each of those carbons form sigma bonds with the carbon atoms on either side of them. So those 2 sigma bonds. One of the sigma bonds is formed between the carbon atom and the hydrogen atom, yeah? So the third sigma bond, yeah. 3 of these electrons form sigma bonds. Then this forms the skeleton of a molecule, giving a planar hexagonal ring. So this is our planar hexagonal ring, yeah? This is it, yeah? So remember, let's say this is a carbon, and a hydrogen. So there's 1 sigma bond here between the carbon and the hydrogen, and then each carbon forms sigma bonds with the carbon atoms on either side of this carbon atom. So 1 here and 1 here. Yeah, so 3 sigma bonds. Now this forms the skeleton of the molecule, this is a planar hexagonal ring. This gives a planar hexagonal ring. Each carbon now has 1 unused electron, because we've used 3 in sigma bonding, so 1 used that's found in the p orbital. Because if we look at the number of carbon atoms, 1s2, 2s2, 2p, 2, yeah, because 6 electrons, right? So 2 is found in the p orbital, because 1, 2, 3, these are the 2 orbitals that we're interested. Sorry, not orbitals. These are 2 sublevels that we're interested in. 3, so the 4th one has to be in the 2p sublevel. Now it's in 2px, which is the orbital, but it's in the p orbital. So so each carbon atom has one used electron that's found in a p orbital. The p orbital is at right angles to the planar molecule. It's at right angles to the planar molecule, right? The lobes of these p orbitals fuse sideways, yeah, to form a single ring of charge above and below the sigma bonded skeleton, and these are pi bonds. Within these pi bonds, the electrons are free to move, which means they're delocalized, which means the electrons are free to move localized are held between two atoms not free to move. Delocalized electrons are allowed to move freely between several bonded atoms. So they're allowed to move freely between several bonded atoms. Yeah, allowed to move freely between several bonded atoms. So they're delocalized. It is this delocalization that causes the carbon-carbon bonds in benzene to be similar and makes the molecule unexpectedly stable. We know that benzene is unsaturated, means contain a multiple bond between carbon atoms because it has a bond that's neither a single bond nor a double bond, but of an intermediate length between the two of them. So essentially what happens is each carbon, 4 electrons in the outermost shell, 3 involved in a sigma bond, 2 sigma bonds with the carbon atoms on either side of that carbon atom, 1 sigma bond with the carbon and the hydrogen. Therefore, each carbon in the sigma bonded skeleton has 1 electron that's free, one free electron, yeah, one unbonded electron. What's it called? One unused electron, right? So this one unused electron, where is it located? It's located in the p orbital, which is at right angles to the sigma bonded skeleton. Now these p orbitals are going to fuse at right angles to the skeleton to form a single ring of charge above and below the sigma bonded skeleton. And in this ring of charge, the electrons are allowed to move freely in this ring. So they're delocalized electrons, meaning that the electrons are free to move between several bonded atoms. They're allowed to move between several bonded atoms, exactly. They're not localized, unlike the sigma bonds, So it is this pi bonding, it is this delocalization which makes the carbon-carbon bonds in benzene similar, and therefore making it unexpectedly stable. So if we come here, so we can see that the carbon-carbon bonds in benzene are neither single bonds nor double bonds, but of an intermediate length between the two. Hence, benzene undergoes substitution reactions, typically, not addition as you would expect from it being unsaturated. And just draw the circle, otherwise it'll be cyclohexane, yeah? And then 2011 question 8. So if we go to just leaving cert 2011 question 8 LC Chem high level. So we for the monochlorination of methane. Monochlorination of methane would be free radical substitute state 3 p express. So ethene can be fast organic reaction. Describe the bonding in benzene, right? So we know that each carbon, benzene has 6 carbons. Each carbon in benzene has 4 electrons in its outermost shell. 3 of those electrons are involved in sigma bonding. Each carbon is bonded, so 2 sigma bonds are formed when each carbon is bonded to the carbon atom on either side of the carbon atom, the 2 other carbon atoms. Then 1 sigma bond is formed when the carbon atom is bonded to the hydrogen atom. This leaves 1 unused electron in the outermost shell of each carbon atom, which is found in the p orbital. The p orbital is found at right angles to the sigma bonded skeleton. Now the p orbitals are going to fuse sideways to the sigma bonded skeleton, forming a single ring of charge above and below the sigma bonded skeleton. Within this ring, the electrons are free to move. Therefore, they are delocalized, which means electrons are free to move between several bonded atoms. And it is this delocalization which makes the carbon-carbon bonds in benzene similar, and therefore making it unexpectedly stable. So, we know the carbon-carbon bond in benzene is neither a single bond nor a double bond, but is of an intermediate length between the two. This means that although a benzene is unsaturated, it actually undergoes substitution reactions rather than ionic addition reactions. Which is pretty cool. Yeah. So we grasped that pretty quickly. So shocking. So benzene is a planar molecule, and it is non-polar. Therefore, it's not soluble in polar solvents such as water. It's not form hydrogen bonds with water, but it is readily soluble in non-polar solvents such as cyclohexane. Then benzene is inside. Yeah, so benzene is then insoluble in water, as it is a non-polar, as not for hydrogen bonds with water. Why is it non-polar? Because its poles of slight positive and slight negative do coincide. Whereas polar molecules, their poles of slight positive and slight negative do not coincide. Yeah, and it is used. So benzene, we know benzoic acid, right? Benzoic acid uses a food preservative. It used to be used as an organic solvent, but it's carcinogenic, which means it's a cancer-causing agent. So methylbenzene or toluene is used to make so methylbenzene I use. So yeah, whatever. I don't really care about that shit. Okay, so now it says experiment. So first of all, what is this? This is the extraction of clove oil from cloves. The extraction of clove oil from cloves. The extraction of clove oil from cloves using a steam distillation, so steam distillation method, and isolation of the oil from the emulsion using a solvent extraction. First of all, we extract the oil from the cloves using a steam distillation, and then we isolate the oil from the emulsion, yeah, using the solvent extraction. So steam distillation and solvent extraction. So cloves used as a spice in cooking has antiseptic properties. Right? So it's a plant first and foremost. I actually want to do a few more questions on benzene before we get in. So 2018 question 10A. 2018 question 10A. How would you describe demonstrated radicals and initial water? Delocalized are electrons that are free to move between several bonded atoms. How many electrons in benzene are delocalized? 6 electrons. Are involved in sigma bonds between carbon atoms. So we know that right. So 1, 2, 3, 4. 1, 2, 3, 4. So this is giving 2. This is giving 2. So 12 electrons, right? Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we have the 1, 2, 3, 4, 5, 6. Let me just chuck this into Gemini real quick. And if I... Makes me stressed as frick, bro. Yeah, we got it right. Alright, so then, what was the other question? 2023 high level user. Question 10. Bro, I'm dying, bro. I'm dying. hydrocyclization. A single benzene molecule has 42 electrons. Are involved in carbon-hydrogen bonding. Would be 6 electrons. Are involved in carbon-carbon sigma bonding. Would be 12 electrons. Are involved in delocalized pi bonding. Would be 6 electrons. Are involved in carbon-carbon bonding. Would it be 18, I think? Are not involved in bonding. Two by 6 is 12. And if you can do this question. How many electrons are involved in carbon-hydrogen bonding? It's 12 electrons, that's true. Then how many involved in carbon-carbon sigma bonding? 12, 6, 18, and 12. Yeah. Okay. That's good. I'm satisfied with that. So let's just go back. So first of all, we're extracting clove oil. Clove oil is used as a spice in cooking. It's used as antiseptic properties. Clove oil. So we're extracting the clove oil from the cloves using steam distillation, and then isolating the clove oil from the emulsion using a solvent extraction, right? Solvent extraction. So I just feel anxiety, bro. I like my mind keeps on telling me you can't do this, you can't do this, you can't do this, and that's no way to live life. Cause I can't do this, bro. I've been doing this. I've been doing this since I started this journey 2 years ago. I'm not giving up on my exams that easily. Steam distillation. Why is steam distillation used and not some other method? Steam distillation is used as it's a method that relies on the principle. So stimulation is used as it is a method that uses the principle that when two immiscible liquids are together, their boiling point is lower than either of the pure compounds alone. So, because it is a method that uses the principle that when two immiscible liquids are together, their boiling point is lower than So steam distillation is used because it's a method that uses the principle that when two immiscible liquids are together, their boiling point is lower than either of the pure compounds alone. Immiscible means that they don't mix together. And why is this a benefit? They could ask, why would you do this? The reason why we use steam distillation is because therefore we don't have to use high temperatures which could burn the plant material. So now we have something called clove oil. Clove oil, the actual name for it is something called the eugenol. Right? Sorry. OH bang bang bang. So this is eugenol. So it's 7, 8, 9, 10. So C10, 3 being used. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, H12, O2. So it's 164 grams relative molecular mass. So eugenol, let's just draw it again. You're probably not going to ask this year, but it's just good to know it. So O, C, it could be like a short question or something, you never know. Yeah. That's eugenol. Okay, nice. Why do we use steam distillation? Because it's a method that uses the principle when two immiscible liquids are together, the boiling point is lower than either of the pure compounds alone. So therefore, what is an emulsion? Emulsion is when two immiscible liquids are together, where one is dispersed as tiny droplets within the other, throughout the other. When two immiscible liquids are together and one is dispersed as tiny droplets throughout the other. I think the definition is here. An emulsion is two immiscible liquids where one is droplets dispersed where one is dispersed as droplets throughout the other. So an emulsion is two immiscible liquids together where one is dispersed as tiny droplets throughout the other. Now, they could ask you about separating funnel. So how do you draw a separating funnel? Separating funnel is something like this. Yeah, that's it. And you have like a little kind of like stopper there as well, yeah. Oh my bro, I hate this. I don't hate it, but it's not my favorite, like, thing. Not my favorite experiment. My favorite experiment, ethene, ethyne. Like that's probably gonna come up as well. Apparently, people are saying ethene is gonna come up, and then the titration is gonna be the sodium carbonate percentage water crystallization. We'll see how much. What goes on. But yeah, so that's kind of it. So if I come here, I have a steam generator. And then I have something like this, yeah. Then I have kind of like a T-bar. And I have kind of like this. Either you could, one thing it remind me, yeah. Either you could sit at home, yeah, and just cry about it. You could actually get the job done. You know what I mean? And that's the difference, bro. That's the difference on like the mindset. Like I've seen people with mindsets that like they're not gonna make it, and they aim for like the lowest thing. Bro, even me, bro. I struggle with this procrastination shit more than anyone, man. That's why I'm here right now. I could have got I had so much time. I could have got the whole course done all the past papers, bang, but I didn't. It's my lazy bum. But everything works out in the end. So my brain knows that everything works out in the end. That's the problem. It just knows. It just knows that the day it doesn't work out, that's the day I'm gonna stop procrastinating. I know it, and I hope that day is not the leaving cert day. I really do hope. I'm not completely like screwed. Like people are like, oh, you're screwed, bro. You're screwed. Like, nah, cuz. To be fair, it's kind of hard to just do chemistry all day. Like, even though that's not what we're doing, but this is definitely not all day. This diagram is difficult to draw, bro. I can't lie, man. You just kind of have to visualize it. Don't worry. I'm gonna draw it a few times, maybe. And we'll see. God knows this is even a good diagram, but it looks pretty shit. I'm looking at it while I'm drawing it, and I still can't. You know. So basically, we have like a steam generator with water and anti-bumping granules, and then we have a safety tube, and then we have a T-bar, and then we have a T-bar going to steam, going to a pear-shaped flask, which has our cloves and our water, and then it has another T-bar which goes to a Liebig condenser, which is water out, water in, then another T-bar, and then yeah, and he's separating collection flask and it's. Oh yeah, and don't forget the Bunsen burner. How are we gonna generate steam if you don't have a Bunsen burner? Oh my god, bro. Oh my god. Oh my god. How would I draw it if I was in exile? Oh god. This is gonna be bad. But we'll try it. I'll try my best. I'll try my best. Okay, this chapter might be just a bit of Irish. Just get one whole short story done and then we'll come back to this. Okay, so the way it is, it's like I was like, oh, I'm just gonna do chemistry. Yeah, no, that's not happening. Alright, so this is some sort of like a steam generator with anti-bumping granules, I think. Then we have some sort of yes, 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 yes. Okay, I don't think it's gonna look like that, but alright, it's fine, it's fine, it's fine, it's not the worst. I'll labor after, bro. I can't lie, I'm not bothered. How? Oh, yeah, I was right. Don't worry, I'll label it, promise, I promise. Might just make it look like there's something there. That's not terrible. So this is like a safety like tube. This is a T bar. This is a Bunsen burner. This is a steam generator. This is a anti-bumping granules. This is the steam, then travels into cloves of a known mass. Water, T-bar, stopper. This has to be tilted as a Liebig condenser, collection flask. This is a separating funnel. I think that's about accurate. And that has to be more tilted, but other than that, can't really complain, thank God. Oh, bro, I have no clue, man. I'm dead already, bro. I can't lie. Alright, let's go. So, steam distillation was the apparatus was set up for steam distillation and water was added to the steam generator. The safety tube was placed such that the end of the safety tube was below the water level, ensuring that the bottom of the safety tube was well below the water level in the generator. The water should be topped up regularly. The safety tube releases pressure and avoids buildup of pressure, avoids buildup of steam. Releases pressure, avoids buildup of steam, and avoids explosion. So it releases pressure, avoids buildup of steam, and avoids explosion as well. A known mass of clothes was placed in the pear-shaped conductor with some water. Bunsen burner was turned on and steam was allowed to pass through the flask for 40 minutes. The clove oil emulsion passed through the condenser down into the collection flask. Separating funnel. The emulsion was milky color. The emulsion was allowed to cool in a separating funnel. So essentially what I did was so first of all, a set of the apparatus is shown in the diagram. We're going to show that the safety tube, the bottom of the safety tube, is well below the water level in the steam generator, and the water is topped up regularly to avoid the buildup of pressure, to release pressure, to avoid the buildup of steam, and to avoid explosion. Now, I'm going to get a pear-shaped flask with water and cloves of a known mass. I'm then going to turn on the Bunsen flame and allow the steam to pass into the pear-shaped conductor for like 40 minutes. The clove oil emulsion then passes through the Liebig condenser down into the separate down into the collection flask, and this is milky white in color, and then we allow it to cool down in the separating funnel. Basically, yeah. God, that's. So that was steam distillation. Now we have solvent extraction. So we need to kind of isolate that oil from the emulsion. Solvent. Solvent extraction. The boy's productivity has definitely gone down the drain right now. Alright, so some non-polar organic solvent was added to the emulsion in the separating funnel. Cyclohexane and the contents of the separating funnel were shaken vigorously as described in the next point. Then what I'm going to do is I'm going to take the separating funnel, ensure the tap is closed and the stopper is in. I'm going to turn it upside down and open the top. No, yeah. I'm going to invert the separating funnel and open the top to release any pressure that builds up from the vigorous shaking of the solution in the separating funnel. Clamp in an upright position. Now draw off the... So we have now... Deja vu. So yeah, essentially, so some non-polar organic solvent was added to the solution. It was added to the emulsion in the separating funnel, i.e., cyclohexane was added, and the contents of the separating funnel were shaken vigorously. Then we have a safety precaution: is we're going to invert the separating funnel upside down, open the top to release any pressure that may have built up from the shaking. Then I'm going to mount it vertically on a retort stand. We're going to clamp it vertically on a retort stand. Then we're going to draw out the clear aqueous solution into a beaker labeled aqueous, and then we're going to place the organic solution into a beaker labeled organic. Now we're going to then place the aqueous solution back in the separating funnel and wash it out with cyclohexane a few more times, around 3 more times, to ensure that all of the organic... Put the aqueous layer back into separating funnel and wash it with more cyclohexane a couple more times just to maximize the yield of oil collected. The organic layer is in the beaker. It may contain some water. So then we add sodium sulfate and hydrosodium sulfate. Add enough anhydrous sodium sulfate so until it no longer clumps together. If water is present, the anhydrous sodium sulfate is going to clump together. If water is not present and all water has been removed, it's going to clump together. It's just going to settle as a white powder at the bottom. Settle as a dry white powder when all the water has been removed. Swirl the flask for a few minutes, then filter through filter paper to remove the drying agent. Rinse the flask with more cyclohexane and pour through the filter paper. This is to maximize the yield of water. The cyclohexane solvent was then allowed to evaporate off, so by heating it gently, off from the filtrate in a warm place, or in a warm place, such as a fume cupboard. This leaves the clove oil behind. Measure its volume. If given its density, find the mass. To measure tiny volume, use a graduated pipette. So essentially, so we have basically clove oil, cyclohexane plus small. Okay, so I'm just gonna kind of go through this, and then we'll take a break because I'm kind of tired. Can't lie. I think I know what we're gonna do for the break as well. Alright, so first and foremost, what we're gonna do is we're gonna set up the apparatus as shown in the diagram. Now we're going to ensure that the end of the safety tube is well below the level of the water in the steam generator. and we're going to top up the water in the steam generator regularly, as it's going to release pressure, it's going to avoid the buildup of steam, it's going to avoid explosion. So we know we're going to place cloves of a known mass with water in the steam generator, turn on the Bunsen burner, allow the steam to pass through the Perrier flask for around 40 minutes. The clove oil emulsion passes down the Liebeck condenser from the condenser to the receiver, and the emulsion is a milky white color, and we allow it to cool down in the separating funnel. Now we have solvent extraction. So some non-polar organic solvent is added to the solution in the separating funnel. Cyclohexane is added to the emulsion, shaken vigorously in the separating funnel. Now, safety precaution: flip the separating funnel upside down, open the tap to release the pressure that may have built up. Now I'm going to clamp vertically on a retort stand. Draw the clear aqueous solution into a beaker labeled aqueous. Draw the organic solution, which is cyclohexane and the clove oil, into the beaker labeled organic. Then I'm going to place the solution in the beaker labeled aqueous back into the separating funnel, and I'm going to wash it a few more times with cyclohexane to maximize the yield of a clove oil that we get. Now, what's in the beaker labeled aqueous is cyclohexane clove oil, but we still have trace amounts of water. So we're going to add a drying agent called anhydrous sodium sulfate. When there's water present, it's going to clump together. We're going to add enough until it stops clumping together and settles at a dry white powder. Now, we're going to then basically swirl the solution for a few minutes. We're going to wash it with a few more times with cyclohexane to maximize the yield of clove oil. Then we're going to filter it using filter paper. And now in our beaker, we're going to have clove oil, and we're going to have our cyclohexane. Now, how we're going to get rid of our cyclohexane is a volatile liquid, which means it has a low boiling point. So we're going to heat it gently, and we're going to allow it to evaporate off the solution in a warm place. So for example, a fume cupboard, right? And then what's left behind in the beaker is your clove oil. And if given density, you can find the mass, volume, whatever you want, right? So that's it. So eugenol. Immiscible liquids are liquids who do not. Okay, this is answer questions. What is the purpose of the tube marked X? So the tube marked X. The purpose of the tube marked X is it avoids the buildup. It releases pressure. It avoids the buildup of steam, and it avoids explosion. What is collected at Y? It's a clove oil emulsion, and it is a milky white color. One use of clove oil is its use as a spice in cooking. Now, two immiscible liquids are liquids that do not mix together. Name a substance you isolated by steam distillation in the school laboratory and the plant material from which it was extracted. So it was extracted from cloves, and we isolated what 2018. What is an emulsion? Emulsion is two immiscible liquid together where one is spread throughout the other as tiny droplets. Name an suitable organic solvent for use in the liquid extraction of clove oil. A cyclohexane. Other than wearing eye protection, gloves, and a laboratory coat and time, we'll say one safety precaution when using a separating funnel. Oh yeah. So when we add cyclohexane to the separating funnel, and we shake the separating funnel vigorously to mix it with the emulsion, we're going to close the tap and put the stopper in. We're going to show the stopper is in and the tap is closed. Turn the separating funnel upside down and open the tap to release any pressure that may have built up in the separating funnel. How is the clove oil isolated using the liquid extraction? So how is it isolated? Is first of all, we have cyclohexane, we mix it together with the emulsion, and then we mount. Okay, so once we've done all that, we mount it vertically on a retort stand, and we draw the aqueous solution to beaker labeled aqueous. The organic solution was a clove and cyclohexane into a beaker labeled organic. Aqueous solution goes back into separating funnel, washed a few more times with cyclohexane to maximize the use of clove oil. Then the beaker labeled organic has cyclohexane, clove oil, and trace amounts of water. We add our drying agents, anhydrous sodium sulfate. It's a white powder, it clumps together in the presence of water. We're going to add enough until it stops clumping, which means there's no more water present in our organic solution, and therefore it settles as a dry white powder. Now, what happens is then we're going to wash this. We're going to essentially swirl the solution around for a few minutes. We're going to wash the solution a few more times with cyclohexane to maximize the yield of clove oil. Then filter the solution to filter paper to remove that anhydrous sodium sulfate. Okay, yani we've done that. Okay, now what we need to do is we need to get rid of the cyclohexane. So we're going to leave the solution to dry in a warm place. To allow the cyclohexane to evaporate off the solution. So, for example, in a fume cupboard, and now what's left behind in the beaker is your clove oil. Steam distillation, and then they give you this, and they give you the density. You can find the mass over the actual yield over the 100% yield is equal to the theoretical yield multiplied by 100 will give us percentage yield. Yeah. So I think that chapter is done as well, to be honest. Yeah, no, I'm a bit tired, bro, I can't lie, but I kind of just have to keep on going, you know, like I can't really stop. I don't have much time. Bro, I swear, man, I made a mistake, and it's okay. We all make mistakes in life. We all make stupid mistakes in our lives. And we're all stupid. We're all stupid. We're all stupid. Alright, I'll do saponification. So an ester is a molecule where the hydrogen of the hydroxyl group of the carboxylic acid is replaced by the alkyl radical of an alcohol. When the hydrogen of the functional group of the carboxylic acid is replaced by the alkyl radical of an alcohol. What you say? Saponification. So we have glycerol tristearate, then we have sodium hydroxide, which is our base. Then we're going to get sodium stearate, and I don't know what the other product is. Sodium stearate, yani, and we will get. Is there equation somewhere here? Sodium stearate. Bro, come on. Sodium stearate and glycerol. No, I remember doing this in class. Wait. Yeah, I have it here. Nice, beautiful. So essentially, what we have here is reaction. First of all, I'm going to start off with the diagram, then we'll go into the equation. Yani, we'll do all of those things. But yeah, my bro, it's kind of like, it's a bit. We're doing well, we're doing very well. I'm very proud of myself, man. I'm very proud. Got this. Alright. So the way it is yani a hot plate with some sort of like a reaction vessel, some sort of a water bath. You know, I don't settle for average, bro, in my life. I want to see where I can go with this, with this exam. I want to see where I can go. Genuinely, I want to see just where I can go with it. Like, where does God lead me to that, you know? Where can I go? Because, you know, it's a blessing to be in the situation, bro, where, you know, you're so privileged, but then you're still lazy. And, you know, it just breaks my heart, man. So I said, no more laziness. I'm done. I don't want that for myself anymore. Akhi, I don't want that for myself anymore. Yeah. To be in this situation, man, it breaks my heart, man. That's what keeps me going. That's what is keeping me going right now, bro. I don't care, man. I'm getting the H1s, bro. I don't care. No matter what it's gonna take, no matter how many hours now, yani, I'll give it everything. You know? This is ethanol. Trying, bro. I'm trying, man. Mm-hmm. I'm not gonna give up a fight that easily, bro. I'm gonna do better than all of these guys, bro. I'm gonna do better than all of these guys, bro. You'll see me. You'll see me. You'll see me. The reaction of, well, the reality of this life, bro. We need to work hard, but we become too lazy. Too much lazy, bro. I'm using my eyes, bro. I'm meant to be a warrior, cuz. I'm gonna work hard. There's no excuses in life anymore. You get me? The odds may be against you, cuz. Odds may be against you, 100% against you. But you never give up. That's the number one thing. Never in your life do you give up. So, let's look. So first of all, 5 grams of lard. So you have to learn this one, but yeah. So let's say lard. Why is ethanol added? No, ethanol. Excuse me. Ethanol acts as a solvent for the lard. Okay. Lard. So 5 grams of lard, or the limiting reactant. So the lard is the limiting reactant. So 5 grams of lard is added to the reaction vessel. A base sodium hydroxide, 4 grams of sodium hydroxide or potassium hydroxide in excess. So lard, all you have to know is lard is limiting, and the sodium hydroxide is the in excess. And ethanol was added. Ethanol acts as a solvent for the lard, as the lard is insoluble in water. Now, anti-bumping granules were added to the mixture. These absorb the heat from the reaction, thus preventing the violent shaking of the apparatus. So these absorb the heat from the reaction. So the anti-bumping granules, they absorb the heat from the reaction and therefore prevent the vigorous shaking of the apparatus. The apparatus was set up for reflux. This ensures time to speed up the reaction, allows for the complete saponification reaction to occur without losing any volatile material. So reflux, this allows time to speed up the reaction to allow the complete saponification reaction to occur without losing any volatile material. The mixture was heated under reflux for 30 minutes. Wash down the residue on the inside of the reaction vessel. Wash down the residue on the inside of the reaction vessel with a minimum of hot water. Too much hot water will reduce the yield of soap later on, as some will remain dissolved in it. After 30 minutes, the heat was removed and the solution was allowed to cool slightly. List the contents of the reaction vessel at this point. The contents of the reaction vessel at this point is going to be our lard, our ethanol, and our sodium hydroxide, and our anti-bumping granules. So essentially, lard, so we have a reaction vessel, yani lard is limiting, sodium hydroxide is in excess, ethanol is added as it acts as a solvent for the lard. Anti-bumping granules absorb the heat from the reaction, prevent the apparatus from violently shaking. What else is there? We wash down the insides. We wash down the insides of the we wash down the insides of the reaction vessel with a minimum of hot H2O, as using too much H2O will reduce our maximum yield of soap soap later on in the experiment. And the reaction was heated under reflux. Why was it heated under reflux? To ensure time to speed up the reaction, to allow the complete saponification reaction to occur without losing any volatile material. Now, after 30 minutes, the heat was removed and the reaction vessel with a minimum of hot water, soap on. To isolate the soap, we must use distillation, and roughly 2/3. So to isolate the soap, the apparatus was rearranged for distillation. So right now in the reaction vessel, I'm guessing we have lard, we have ethanol, we have sodium hydroxide, we have anti-bumping granules, we have soap, and we have glycerol. Glycerol or propane 1,2,3-triol. Propane 1,2,3-triol. Yeah. Now, what is the equation of this? Is first of all we have glyceryl tristearate. Now remember, this was our lard. This was our limiting reactant. I think I know how to draw it. C17H35 COO, C17H35 COO, and C17H35 COO, C, C, C. They're connected all to each other. They're bonded together. H, 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 H. This to tristearate plus sodium hydroxide is going to give us C17H35 COONA, so sodium stearate, which is our, and then plus propane 1,2,3-triol, or also known as glycerol. So this is going to be So that's like propane. So then the solution in the flask was allowed to cool slightly. So we removed the ethanol, the 2 parts ethanol by distillation, and we learned the diagram for that. This hot solution was then decanted. The solution in the flask was allowed to cool slightly. This hot solution was then decanted quickly into a concentrated salt solution. So a concentrated salt solution, brine. The soap is insoluble in brine, and therefore the soap precipitates out of solution. Anti-bumping granules stay behind as decanting. Using a Buckner funnel. So if we come here, yani, we come here, this is kind of like our soap. This is our brine, which is a very concentrated salty H2O. And this is our soap. And what we had was we had something where we decanted it out like this. This is our anti-bumping granules, yeah. So now we remove the anti-bumping granules, remove the remove the ethanol. Using a Buckner funnel, the soap was filtered and weighed. Was filtered using weighed filter paper. The soap was then washed several more times using ice cold water to remove any sodium hydroxide on the outside clinging to the soap. This is important as it doesn't burn the skin. The soap was allowed to dry on the filter paper in a desiccator. The soap and filter paper were weighed, and the difference in mass is the actual yield of soap. Use moles of lard to determine. So essentially, what we did was we had a reaction vessel, Yani, okay? What did we do? Reaction vessel, we added lard, which was limiting. We added lard, which was limiting. We had sodium hydroxide, which was an excess, ethanol to act as a solvent for the lard, anti-bumping granules to absorb the heat to prevent the apparatus from shaking violently. Then we also we heated the apparatus under reflux in short time to speed up the reaction, to allow the complete saponification reaction to occur without losing any volatile material. Okay, fine. Then what we did was we then washed down the insides of the reaction vessel or the reaction flask with a minimum of hot H2O, because if we use too much H2O, therefore the yield of soap would be decreased later on. So then we know that the 2 parts ethanol was then distilled off using steam distillation. And then we show the diagram for that, Yani. And then, yeah. So what is in a reaction vessel at this point before doing the distillation? We have, of course, lard. We have sodium hydroxide. We have anti-bromine granules. We have propane 1,2,3-triol. We have soap. Yeah. And ethanol as well, yeah. So ethanol is then distilled off. We got rid of the ethanol. So then we're going to allow the solution in the reaction vessel to cool off a little bit. Then we're going to this hot solution was decanted quickly. This hot solution was decanted quickly into a solution of salty, very concentrated salty H2O or brine. The soap is insoluble in the brine, so therefore precipitates out of solution. Then the solution was then filtered using a Buckner funnel, using a weighed filter paper, and then the soap was then washed with ice cold water to remove any sodium hydroxide that was clinging to the outside of the soap, as it could burn the skin. Then we're going to take the soap, and we're going to allow it to dry on the filter paper in a desiccator, and then we're going to then weigh the mass of the soap and the filter paper, and the difference is the mass of the soap, is the actual yield. Yeah, so yeah, that's it. So what is in the brine? Okay, I. What is the principal chemical difference between vegetable and animal fats? Vegetable fats are unsaturated fats, whereas animal fats are saturated fats. Apart from the large sodium hydroxide and ethanol, what else should be added to the reaction vessel prior to reflux? Anti-bumping granules. Anti-bumping granules are going to absorb the heat from the reaction, prevent the apparatus from shaking violently, which is a definite safety feature. What is the mixture reflux? Because heating the apparatus under reflux ensured time to speed up the reaction to allow the complete saponification reaction to occur without the loss of any volatile liquid. Why was ethanol added? To act as a solvent for the lard, as lard is insoluble in H2O. Why is it desirable to remove all the ethanol after reflux? Um, why is it desirable to remove ethanol after reflux? Sapon. Oh yeah, to isolate the soap to maximize our yield. That's what I was going to say. Why was a minimum of hot H2O used to dissolve the residue from the distillation? Why was a minimum of hot H2O used? Because if we used too much H2O, it would minimize the yield of soap that was produced at the end of the experiment. What is brine? Is a very concentrated salt H2O. Describe how the soap could be isolated from a mixture of soap and brine. So first of all, we're going to filter the solution with the soap and the brine through is it a Wade filter paper? I think it's a Wade filter paper. Yeah, it was filtered using Wade filter paper. And then the soap was then rinsed with ice cold water to remove any NaOH or sodium hydroxide that was clinging on the outside of the soap, as that could burn the skin. And then is left to dry in the desiccator on the filter paper, and then you get the difference in the mass. Alright, that's glycerol tristearide. Sodium hydroxide, so propane 1,2,3 triol is this. H. Why is a mixture reflux? To allow time to speed up the reaction to ensure to allow the complete saponification reaction to occur without losing any volatile material. Name the type of reaction which occurs during the reflux stage of the preparation. Saponification or base hydrolysis. Complete the balance, the equation, yeah. Yeah, so, yeah, it's easy enough. Propane 1,2,3 triol plus C17H35 COONA, sodium stearate. But just make sure valency 1 is fine. What's the purpose of the ethanol? It acts as a solvent for the lard, as lard is insoluble in H2O. Why is it desirable to remove ethanol after reflux? To remove impurities, to maximize our yield of soap at the end of the experiment. As it is an impurity, describe with the aid of the label diagram how you remove the ethanol after the reflux stage of the experiment. So very simple. We have yani hot plate, water bath, reaction vessel, uh, T-bar at a slant like that. Yeah, nice. And then we have something like this, and then we have some sort of like a I did that wrong. That should be up until there. Some sort of thermometer, some sort of anti-bumping granules, then some sort of yeah, no friends. How do you do it? Like, oh yeah, bro. What do you do? How do I study this much, bro? Like, crazy. Alright, so this is my reaction vessel. This is my this is my hot plate. This is my anti-bumping granules. Oh yeah, don't forget to just do something like this. This is my T-bar. This is my thermometer. This is my Liebig condenser. And this is my collection flask. This is ethanol, which is my filtrate. Okay. Describe the pure sample of soap was obtained from the reaction mixture. Allow the reaction mixture to cool a bit. Then pour the hot solution, decant the hot solution quickly into a beaker. And decanting is going to remove the anti-bumping granules as they remain back in the reaction vessel. Then we're going to decant it quickly into a beaker of brine, which is very concentrated salty H2O. As the soap is not soluble in lard, it's going to precipitate out of solution. Then we're going to filter this solution using a weight filter paper into a beaker. So then the soap is then going to be washed with ice cold ethanol. No, sorry, ice cold water. It's not biology. It's not the isolation of DNA from plant tissue. Okay, no. Yeah. So we're gonna isolate that. We're gonna rinse it with ice cold water to remove any free sodium hydroxide clinging on the outside of the soap, as it could burn the skin. And then we're just going to place it on filter paper to dry in a desiccator, and then we're just going to get the difference in the mass, and then we get the mass of the soap. Okay, at the end of the experiment, what is the location of the second product of the reaction? Brine. Of the excess sodium hydroxide? Brine. What would you observe upon shaking if a little soap of the prepared in this experiment is added to a test tube containing deionized water? Oh, yeah. So C17, H35, COO minus Na plus. Oh, there's some bullshit with this as well, yeah? What would you observe? Oh my god, thank god I saw this question. So this is so this is ionic or polar because ions, but this is a non-polar. It's a very long carbon chain that's non-polar. Of course, this is going to be hydrophobic, but that's going to be hydrophilic. And this is going to be hydrophilic. This is going to react with the sweats. And it's going to react with the oil. So, ionic, polar, very long, non-polar carbon chain. The ionic part reacts with the sweat because sweat is water, if you think about it. And then the non-polar reacts with the oil. And then, yeah. Alright, bet. Hydrophilic is the one that loves the water. Hydrophobic is like, oh, nah, I don't engage in that. But, okay. So then it says a test tube containing... What if sodium? What if why is my keyboard sticky, bro? I think the rubber. Oh, because there's white tack at the bottom of my stupid keyboard, man. I don't know why. I don't know where that came from, bro. I can't lie. Alright. Okay. So then I'm like, okay, what happens if sodium stearate was added to mineral water from a limestone region? Oh man, Gemini, please, I need to go toilet, bro. Please, Gemini. Oh, Gemini, oh, please help me. I'm trying to go to the toilet. Mineral water from... so it's hard water. Produces scum. So could I do C17, H35, COONA plus That's probably what they're gonna ask. Yeah. Alright, that chapter is done as well, which is amazing. It's cool that it was done that quickly. I don't know how, I don't know where, I don't know how, but it just was. And yeah, so I need to go to the toilet, so I'll be back. I'll be back, I'll be back, I'll be back. And alright, you guys, hey, how's it going? We're nearly at 3.5 hours. I think this is the most I've ever streamed, so this is great. Oh, we're just gonna study this mandatory experiment. Well, doxing myself. I don't really care about doxing myself at this point because, like, I don't even go to the school anymore. Yeah, so like, I don't really care, to be honest. Alright, because school's over now. If school was still going on, then I would care about doxing myself. But alright, so let's just go to recrystallization experiment, finding the pure melting point. Is it pure? Is it impure? So recrystallization, yani we got that all there, and then yeah, let's go for it. So essentially, the way we do this is very simple. So oh man, Oh man, very young. Just build different, cuz just build different. Oh man, this pencil is so tiny, man. What the hell? Is there no bigger pencils? Well, this one's a little bit bigger, I think. I'll just throw the titration thing in the bin. Work on that. You think you're screwed? Bro, I don't think I'm screwed, but can't lie. Okay, so it says Bender experiment. So this is the preparation of benzoic acid. Yeah, preparation of benzoic acid. Okay, so preparation of benzoic acid is basically oxidation of a substance called phenylmethanol to benzoic acid. So oxidation of phenylmethanol, oxidation means loss of electrons, so to benzoic acid with KMnO4 in alkaline conditions. Why alkaline conditions? Because we have a faster rates of reaction. So faster rate of reaction. So phenylmethanol is phenylmethanol is getting oxidized. Phenylmethanol is getting oxidized to benzoic acid using KMnO4 and potassium manganate 7 solution in alkaline conditions. Alkaline conditions, why? Because it's faster rate of reaction. So basically, the way phenylmethanol looks is basically one of the hydrogens been replaced with a benzene group. So now it's an aromatic compound. So if we come here, oh shit, I wrote ethanol, phenylethanol. Okay, we can redraw it. No, it's fine, it's fine, it's fine. I'm gonna start feeling hungry as well in a bit. So that's it. That's it. That's as simple as it is. Now, theory behind the experiment is an alcohol is oxidized in alkaline conditions to an aldehyde, then is oxidized to a carboxylic acid. The alcohol uses phenylmethanol, then be oxidized to phenylmethanol, then be oxidized to benzoic acid. The oxidized agent is potassium manganate 7, so Mn plus 7, which is purple. And the alkaline conditions are provided using use of sodium carbonate for alkaline conditions. It's too many sodiums. Sodium sulfate, sodium hydroxide in the last experiment, and now sodium alkaline conditions. Now, excess potassium manganate 7 is excess, and this is in excess, is used to provide show the complete oxidation of phenylmethanol to benzyl alcohol. No, sorry, to benzoic acid. Otherwise, you will end up with phenylmethanol. The potassium manganate 7 will itself be reduced to a brown precipitate. So this will be reduced to Mn plus 4. So MnO2. Now, hydrochloric acid is now added to precipitate the crystals, neutralize the sodium carbonate, and the potassium hydroxide used. Potassium. When was potassium hydroxide added? Cuz, bro, what? Hydrochloric acid is now added to precipitate the crystals, so to make them no longer soluble in the solution, so that we actually get the physical crystals, to precipitate them out of solution, to neutralize the sodium carbonate. Yeah, I know sodium carbonate is for the alkaline conditions, but what's potassium hydroxide for? Okay, and protonates the benzoate anion to form benzoic acid as the solution cools. So HCl is added to precipitate the crystals. To precipitate the crystals, to protonate protonate the benzoate ion, benzoate ion to benzoic acid as the solution cools. To protonate benzoate ion to benzoic acid as the solution cools, to precipitate the crystals out of solution, and to neutralize the sodium carbonate and potassium hydroxide. Yeah, potassium hydroxide. So to protonate sodium carbonate and potassium hydroxide. To neutralize the sodium carbonate used and potassium produced. So sodium carbonate used, produced. It's produced. It's a product. Yeah. So phenomethanol. First of all, phenomethanol. It's a colorless, oily liquid. So phenomethanol is going to be limiting, whereas the KMNO4 is going to be an excess, and then we're going to produce benzoic acid plus the MnO2, which is the brown precipitate. We're going to produce the KOH, and we're going to have this, and water as well. Do I have to know the equation, bro? Did they ever ask the equation? Yeah, I should know the equation. Okay, so phenylmethanol. Excess KMNO4 and 0.5 grams of sodium carbonate is going to create the alkaline conditions, faster rate of reaction. Concentrated KMNO4. Sodium carbonate is used to rate of reaction increase. If a complete oxidation does not happen, a brown smell of almonds will be noticed as phenylmethanol will be oxidized to phenylmethanol. The flask was placed in a water bath for 20 minutes. This aids the full oxidation of benzoic acid. So placed in a water bath for 20 minutes. Then note that the color change of Mn plus 7, purple to dark brown precipitate. Now, if after 20 minutes there's still a smell of almonds, we add more KMNO4. No, heat some more. So we heat some more. So wait, so we said we placed it in a water bath for 20 minutes. This aids the full oxidation. Then 4 centimeter cubes of HCl is added to neutralize the sodium sulfate. Sorry, what's it? Sodium sulfate? Sorry. Sodium carbonate that was added and the potassium hydroxide that was produced. HCl is also going to allow the crystal to precipitate out of solution, and it's also going to protonate the benzoic acid to form benzoic acid while the solution cools down. Okay, and it protonates the carboxylate ion. What was it? That was carbonium. This is carboxylate. A glass rod was dipped into crystals. This was then touched with blue litmus paper. The paper should turn red due to the presence of benzoic acid. Bring contamination crystals with brown MnO2. It's dissolved in 10 of so MnO2 is dissolved in sodium sulfite. So sodium carbonate, sodium sulfite. Heat if necessary. When all the conical flask was placed on ice and the benzoic acid recrystallizes. The crystals were filtered. They're washed with ice water to maximize the yield. Okay, and the crystals are dried in a desiccator. The purity of crystals determined. What the frick? Alright, let's just do Leaving Cert 2015 and let's just leave the rest. So it's colorless, oily liquid. Color change is going to be when phenomethanol is heated with potassium manganate. Easy. So B is purple to brown precipitate. Identify A and B in the reaction scheme. Well, I want to understand. So we have so what is this compound here? Is it organic tan? It is organic tan. I just open it up here, bro, so that I don't cheat off that shit. Yeah, so here it says identify A and B in the reaction scheme. So A is C single bond O minus N plus Na plus. So B is sodium sulfate. Is it sodium sulfate or sodium sulfide? Sodium sulfite. Okay, sodium sulfite. A there in the reaction scheme. So what does HCl do? It allows the crystals to precipitate out of solution. It neutralizes the sodium carbonate added at the start and the potassium hydroxide produced at the end. And it also protonates the protonates the carboxylate ion. Oh man, just show me the carboxylate ion, man. C double bond O single bond O. Oh bro. Oh my god. C double bond O single bond O. Is it that A? That's it. This is a carboxylate ion. That's what it looks. C double bond O single bond A. HCl. Yeah, okay. What changes were observed in the reaction vessel on the addition of these two chemicals? On addition of HCl, the crystals precipitated out of solution. On the addition of sodium sulfite, the brown precipitate disappeared and the solution turned colorless. The brown precipitate dissolved and the solution turned colorless. What changes were observed? State the change in the oxidation numbers of manganese during the experiment. So it went from Mn plus 7, which is purple, in potassium permanganate 7 solution. Then it went to Mn plus 4, which is our brown precipitate. Then it went to Mn plus 2, which is our colorless. Yeah. Then it says after isolation by filter vessel as were purified state, the one way of maximizing the yield of the recrystallization process. Okay, so I'll just do this part and then I'll go to the recrystallization. Describe the appearance of phenolmethanol. It's a colorless, oily liquid. Name a suitable piece of apparatus to measure accurately 1.5 centimeters cubed. Say a graduated pipette. How does the appearance of the reaction mixture change when the phenolmethanol is heated along with purple to brown precipitate? So stage D, when sodium sulfide is added, the brown precipitate E is caused by recrystallization. Describe how you measure the melting point. Bro, I'm just tired, man. But this is what happens when you're so kind to yourself and you don't study earlier. So first of all, just want to check something. Okay, so now we have recrystallization. So I believe it was phenylmethanol. Phenylmethanol plus KMNO4 is going to give us KOH, water, MnO2, MnO2, and benzoic acid. Yeah, recrystallization. So benzoic acid is, so we know so benzoic acid is very soluble in hot H2O, but it's less soluble in cold H2O. Very soluble in hot H2O, but less soluble in cold H2O. So we're going to dissolve the benzoic acid crystals in a minimum of hot H2O, because more crystals. So dissolve benzoic to use filtration under suction to remove the insoluble salts. So filtration under like suction, sure. Benzoic acid. To maximize yield of. So we're going to dissolve it in a minimum of hot H2O. We're going to dissolve it in a minimum of hot H2O. And then we're going to place the benzoic acid. We're going to allow the benzoic acid to cool in an ice bath to maximize the yield of benzoic acid crystals that recrystallize. Now, suitable technique, recrystallization. Dissolve the impure benzoic acid crystals in a minimum of hot H2O. The melting point range, so they tend to like the melting point thing, yeah. So to see if crystals are pure through melting points. See if our crystals are pure through, like, let's say melting points, right? So we have basically pure and impure. So pure would be sharp melting point and higher melting point, whereas impure would be melting point range and lower melting point. If it's broad, less pure, narrow, more pure. Bro, I feel sick, man. I feel like vomiting. Oh my god. This is bad. Bro, I thought we were on the come up, bro. So pure benzoic acid crystals have a sharp melting point and a higher melting point. Impure benzoic acid crystals have a lower melting point and a melting point range. Then in the melting point range, if it's a narrow range, it's more pure. If it's a broad range, it's less pure. Yeah. So we have paraffin oil. We have a Bunsen burner. We have a thermometer, right? The thermometer, right? So you have some sort of a thermometer, and we have a capillary tube that's like attached to that. So melting point tube that's attached to that. It's a boiling tube, paraffin oil, thermometer, rubber band, and then we should have a stir as well, yeah? So, okay, let's do it. So this is a Bunsen burner, boiling tube. This is my, inside here I have my paraffin oil, and this is my capillary tube. This is my stir. This is my thermometer. So what do I do? So I'm going to allow set up the apparatus as shown in the diagram. Set up the apparatus as shown in the diagram. Heat gently, stirring for uniform heat distribution. On observing a visible meniscus, record the temperature. So first of all, we're going to set up the apparatus as shown in the diagram. We're going to heat gently, and we're going to use the stirrer to ensure a uniform heat distribution. And upon seeing a visible meniscus in the capillary tube, seeing a visible meniscus, record the temperature. Set the apparatus, heat gently with the Bunsen burner, and stir to inform uniform heat distribution. And upon seeing a visible meniscus, record the temperature. Paraffin oil is 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 paraffin oil colorless? Yes, paraffin oil is colorless, and it has less impurity. It has a higher boiling point. So the reason why we use paraffin oil is higher boiling point than water, and it's also has no color, colorless. So has no color, and is a higher boiling point than water. Heat gently, stir to ensure uniform heat distribution. And upon seeing a visible meniscus, record the temperature. We have another chapter under our belt. Organic 10, yeah? Bet, bro, bet. Kindly, I might go and eat something, and then we can grind after. Okay, let me pause. I'll be back. What's going on, guys, and welcome back. Just need to change this topic thing. Then you realize, bro. So I think what we're gonna do is we're gonna switch up the gears. And I'm on chemistry. I think I'm gonna do a bit of atomic theory 7 and atomic theory 6. So I'm gonna do mass spectrometry, and I'm gonna do ionization energy as well. Yeah. Alright. Alright. Bet. Bro. Rates of reaction I hate with a passion. What's atomic 6? We can put this away for now. Oh, and don't forget this benzoic acid crystals in your sample. Yeah, okay. Right. So something is moving and you subject it to a sideways force. So the mass spectrometer is an instrument that helps to investigate the presence and abundances of the isotopes. So isotopes are atoms of the same element, which have the same atomic number but different mass number due to the difference in the number of neutrons in the nucleus. So isotopes of an element and the masses of the molecules inside there is a vacuum, so that it is possible to produce the study of ions that otherwise do not exist. You just have to learn this, but don't bother with all this. Like, I've already read that over. That's more understanding shit. But right now, so what's the principle? This principle states that involved is that the different ions are separated according to their masses, the mass charge ratio, and moving in a magnetic field. So the principle is different ions are separated based on their different masses when passing through. So different masses, so mass charge ratio. So different ions are separated based on their different masses or mass charge ratio when passing through a magnetic field, when moving through or passing through. Excuse me, when moving in a magnetic field. So the principle of the mass spectrometer states that the different ions are separated different ions are separated based on their different ions are separated based on their different masses or mass charge ratio when moving in a magnetic field. So the mass spectrometer usually asks for two. What is the uses of the mass spectrometer? So first of all, we know the principle of the mass spectrometer is the different ions are separated based on their different masses or charge mass ratio when moving in a magnetic field. Then we said, what are the uses of a mass spectrometer? What's the use? Like, why are we doing this? I'll do this. I'll do ionization energy, and then I'll do rates of reaction, because that's kind of a weak topic. And then everything else I kind of know. So that'll definitely increase the confidence level, bro, for sure. So use of mass spectrometer is to identify the presence of different isotopes in a sample. To identify the presence of different isotopes in a sample, of course. To show the relative abundances of the isotope of an element. The average mass of an atom of an element compared to 1/12 the mass of the carbon-12 isotope, taking the relative abundance of the naturally occurring isotopes into account. To show the relative abundance of the isotope of an element. To calculate the relative atomic and relative molecular masses. And helps in identifying compounds if they come from an unknown source. So to identify isotopes present in a certain compound, to identify the presence of different isotopes in a sample. So to identify the presence of different isotopes in a sample, to determine the relative abundances of isotopes. To show the relative abundances of isotopes of an element, to determine the different isotopes of an element present in a sample, to show the relative abundances of isotopes of an element, to calculate the relative atomic and relative molecular masses, and it helps in identifying compounds from an unknown source. So to identify the different isotopes in a sample, to identify the presence of different isotopes in a sample, to show the relative abundances of isotopes of an element, to calculate the relative atomic and relative molecular masses, and to identify elements in a compound if the source is unknown. It helps in identifying compounds if the source is unknown, if they come from an unknown source. It helps identifying elements. It helps in identifying compounds if they come from an unknown source. It helps in identifying compounds if they come from an unknown source. It helps in identifying compounds if they come from an unknown source. So the principle of the mass spectrometer states that the different ions will be separated based on their different masses or mass charge ratio when moving in a magnetic field. Uses of the mass spectrometer is to determine the different isotopes present in a sample, to show the relative abundance of isotopes of an element, to calculate the relative atomic and relative molecular masses, and to identify compounds if the compounds come from an unknown source. It helps to identify compounds if they come from an unknown source. I feel like none of that's gonna stick, bro, but I bet. Okay, so we have kind of like a few stages here. I remember my teacher replaced one of them with another thing, so I think deflection was actually something else. This is 6. Should have it, bro. Come on. Bro. Cuzzy, bro. Where is it? It's actually kind of annoying now, bro. It's kind of trolling. You gotta. To identify the different isotopes present in a sample, to show the relative abundances of isotopes of an element, to calculate the relative atomic and relative molecular masses, and to help identify a compound if the compound comes from an unknown source. Wow. Okay, alright. So now we have the 5 steps. Yeah? First of all, we're going to start off with vaporization. Now, what is vaporization? So the substance is injected into the mass spectrometer that contains a vacuum. The high temperature vaporizes the substance. To move through the machine, the particles must be in the gaseous phase. So vaporization is the substance is injected into mass spectrometer so the substance is injected into mass spectrometer, which contains a vacuum. Now the substance then vaporizes. The high temperature vaporizes the substance. This causes electrons to move through. So first of all, we have vaporization. So the substance is injected into the mass spectrometer, which contains a vacuum. The high temperatures vaporize the substance. In order for the substance to pass through the machine, it must be in the gaseous phase. In order to move through the machine, the particles must be in the gaseous phase. So vaporization is the first step. Then we have production of positive ions. So an electron gun is going to fire high energy electrons at the vaporized substance. So an electron gun is going to fire high energy electrons, gun, fast, high energy. So high energy electrons at the vaporized substance. This causes electrons in the vaporized substance to be removed, knocked out of orbit, and thus forms positive ions. This causes the electrons in the vaporized substance to be removed or knocked out of orbit and thus forms positive ions. So electron. But where are they getting electron gun? Like electron gun fires high energy electrons. So electron gun, it fires high energy electrons at vaporized substance. This causes electrons in vaporized substance to be removed or knocked out of orbit. This causes electrons in vaporized substance to be removed or knocked out of orbit. Yeah. So first of all, we have vaporization, substance injected to the mass spectrometer. The high temperatures vaporize substance, and in order to pass through the machine, the particles must be in the gaseous phase. And we have production of positive ions. So electron gun fires high energy electrons at the vaporized substance. This causes these electrons cause the electrons in the vaporized substance to be removed or knocked out of orbit to form positive ions. Then 3 was acceleration. There's some like magnetic plate, I'm pretty sure, acceleration. So vaporization, production of positive ions, acceleration, deflection, separation, and detection. Acceleration is, so the spectrometer contains negatively charged plates or a grid, right, that attract positive ions and causes these. So many days, man, that are just gonna be wasted as well. Okay, so the spectrometer contains a negatively charged metal plate or grid that attracts the positive ions, causing the positive ions to accelerate, to move at high speeds, and concentrates them into an beam. And oh man. So the spectrometer contains a negatively charged metal plate or grid which attracts the positive ions, which causes the ions to move at a very high speed and concentrate into a narrow beam. Then we have separation. So the beam of positive ions is then deflected. Beam of positive ions is then deflected by beam of positive ions is then deflected by magnetic field. The lighter particles deflect readily. Lighter particles, of course, yeah, deflect. Beam of positive ions is then deflected using a magnetic field. The lighter particles deflect readily, heavier particles not so readily, less readily. So ions are now separated for their heaviness slash mass. Oh, bro, I'm tired, man. Why did I do this to myself? I'm such an idiot. I'm such an idiot. Bro, lock in. So 16 days. 16 days today. Okay, so first of all, vaporization. Substance is injected to the mass spectrometer. High heat vaporizes the substance. Substance must be in the gaseous phase to pass through the system. Now we have production of positive ions. So electron gun fires high energy electrons towards the vaporized substance. These electrons knock the electrons out of they remove the electrons from the vaporized substance or knock them out of orbit, forming positive ions. Then we had acceleration. Acceleration is the spectrometer has a negatively charged plate slash grid which attracts the positive ions. Positive ions then move at very high speeds and it can concentrate into a narrow beam. Then we have separation. So the narrow beam of positive ions is then deflected by magnetic field. The lighter particles they're deflected more readily. The heavier particles deflected less readily, and basically the ions are separated based on their mass. Yes. And detection, finally. They're gonna. Bro, this is bullying, bro. Detection. These particles then hit against the analyzer. They hit against the analyzer, which sends different impulses to the recording device, which shows up as a series of lines and peaks on a piece of paper. So these particles then hit the analyzer, sends different impulses to the recording device, which shows up as a series of lines and peaks on a graph, on a piece of paper. The resulting picture is called a mass spectrum. The detector counts the number of different ions hitting against it and therefore can measure the relative abundance of each type of isotope. The number of different ions hitting against and therefore can measure the relative. So detection is these particles then hit against an analyzer, sends impulses to a recording device, which creates a graph with lines and peaks on a piece of paper, which shows up as a series of lines and peaks on paper. The resulting picture is called a mass spectrum. The detector counts the number of different ions hitting the analyzer and therefore can measure the relative abundance of the different isotopes. So last but not least, what was the principle of the mass spectrometer? That the different ions are separated based on their different mass or mass change ratio when moving in a magnetic field. Then we talked about what is the use of it. First of all, is to determine the different isotopes that are present in a sample, to show the relative abundance of isotopes of an element, to calculate the relative atomic mass or relative molecular mass, and to identify a compound if it comes from an unknown source. Then we said vaporization, substance is injected into the mass spectrometer. High temperature cause the substance to vaporize. Then in order to move through the system, the substance must be in the gaseous phase. Then we have the production of positive ions. So electron gun fires high energy electrons towards the vaporized substance. These electrons remove the electrons from the vaporized substance or knock them out of orbit, forming positive ions. Then we have acceleration. So in the mass spectrometer, there's a charge grid or plate which is which is negatively charged, and this attracts the positive ions. Positive ions then travel at very high speeds and get concentrated into a narrow beam. Then we have separation. So the narrow beam of positive ions is then deflected by a magnetic field. The lighter particles deflected more readily, heavier particles less readily. So the particles are separated based on their mass or mass charge ratio. The different ions are separated based on the different masses or mass charge ratio. Then we have detection. These particles then hit against an analyzer. Analyzer is going to send impulses to a recording device, which creates a series of lines and peaks on a piece of paper, which is called a mass spectrum. And this tells us the number of different types of ions hitting it, and therefore we can calculate the relative abundance of each isotope present. No, this. Oh man, this is some bullshit, bro. This is some actual bullshit. Like, oh man, oh man, I need help. I need help, bro. Um. Oh, okay, wait. Organic 7 I'll do later. I think oh no, we did theory 6. We didn't do theory 7, did we? No, we did theory 6. So I just did theory 6 there. So I'll just do theory 7 now. Ionization energy. The first ionization energy, the minimum amount of energy needed to remove the first loosely bound electron from a group of atoms of an element in their standard gaseous ground state, something like that. Wait, yeah, we'll double check. Alright. And then where's organic 7? Cuz I don't want. Did I download organic 7 by accident? I'm stupid, bro. Like, I don't know what I'm doing. Alright. Ionization energy. So first ionization energy. This is the minimum amount of energy required to remove the first loosely bound electron from a bowl of isolated atoms in their gaseous isolated atoms of an element in its neutral gaseous ground state. The minimum amount of energy needed to remove the first loosely bound electron from a group of isolated atoms of an element in their neutral gaseous ground state. The minimum amount of energy needed to remove the first loosely bound electron from a mole of isolated atoms of an element in their gaseous neutral ground state. Trends in the periodic table. Okay, so if we go to the periodic table, we can see we have to look at trends in electronegativity and trends in the atomic radius. So we know that as we go across a period, what happens? The atomic radius gets smaller, right? The atomic radius gets smaller, and the electronegativity gets larger. Now, Why is that? Because first of all, why would this atomic radius get smaller? Because the nuclear charge or the number of protons in the nucleus is increasing, whereas the screening effect of the electrons in the incompleted shells on the outer electrons remains the same. So therefore the nucleus has a stronger pull on the outer electrons, thus pulling them closer towards itself and therefore smaller atomic radius. Whereas as we go down a group, let's say, atomic radius increases. Why? Because first of all, uh, the nuclear charge or number of protons in the nucleus remains the same. However, the screening effect of the electrons in the inner completed shells and the outer electrons is increasing. So therefore, the electrons in the inner completed shells block some of the pull that the nucleus has on the outer electrons, thus a larger atomic radius. So we know electronegativity values are going to increase as we go across the period. They're more firm. Outer electrons are more firmly held, whereas going down a period, they're getting less firmly held. The outer electrons are further away from the nucleus, the less firmly held, and thus the energy removed and decreased. So we have basically ionization. So ionization energy, there's four factors. So I'm going to say one of them was atomic radius. One of them, are you removing it from an electron from an atom, the first newly bound electron from an atom, or are you moving it from an ion? The like the arrangement of the sub levels, right? Do you have a full sub level, a half fill sub level, or do you have anything in between, which is the least stable? And then stability of the sub level, stability of the energy level. The noble gases will have the highest first ionization energy, as they're unreactive because they tend to have an arrangement of 8 electrons in their outermost shell, except for helium, which has 2 electrons in its only outer shell. So, therefore, they're very stable. Alkaline metals, we know they react vigorously with water to produce metal hydroxide and hydrogen gas, burn in oxygen to form metal oxide. You know, they react vigorously. They're shiny and freshly cut, tarnished due to contact reaction with the rapidly due to reaction with the air. So all these different things. So they're very reactive. Lowest first ionization energy, as they only have one electron atom shell, will lose it very easily to attain a stable configuration. Full shells are very stable. Are so stability of a sublevel, removing from an atom versus an ion as well. So leaving sir 1988. Okay. Write the electronic configuration for atoms of nitrogen, phosphorus, and sulfur. So nitrogen is 7 electrons. Phosphorus is 15 electrons. And sulfur is 2, 2s2, 3. No, so it's 2p3. I just feel, bro, I'm not good enough, man. But nah, I'm not giving up. 2s2, 2p6, 3s2. So that's like yeah, and then 3p what? So 2 4 that's 10. 3p3. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Yeah. Okay. 16. 1s2, 2s2, 2p6, 3s2, 3p4. And just add like some commas and stuff like that, yeah. Yeah. So now it says account for decrease in the first ionization energy. So decrease from decrease from nitrogen to phosphorus. So what are the 4 factors? I'd always write this down. So atomic radius, um, electron arrangement, sub-level arrangement, RV remove, so decrease from nitrogen to phosphorus. So in terms of the atomic radius, we know the atomic radius decreases. Increases as we go down a group. So first of all, the atomic. No, atomic radius of phosphorus is bigger than atomic radius of nitrogen. So nuclear charge is increasing as you go down, yeah, but nuclear charge so don't mention nuclear charge going down there. Okay, so atomic radius of phosphorus is bigger than the atomic radius of nitrogen. Therefore, in phosphorus, the outer electrons are less firmly held. Therefore, the first loosely bound electron, is less firmly held by the nucleus compared to nitrogen, where the first loosely bound electron is held more firmly due to pull of nucleus as atomic radius is smaller. So sub-level arrangement, their sub-levels are the same. They're both half filled, so there's no effect there. Atomic radius of phosphorus going down a group, atomic radius increases. So therefore, we know that the nucleus of phosphorus, the first loosely bound electron in the outer shell, is going to be less firmly held when we look at the first loosely bound electron in nitrogen, which is going to have a stronger pull on that. So that's what we said. We said we're moving from looking at our electron arrangement. I mean, they're in the same group, so therefore the same number of electrons in their outermost shell, which is 6, which is 5. 5. Nothing else has an effect. Okay, so from phosphorus to sulfur. So phosphorus So first of all, atomic radius. Actually, we know atomic radius decreases. From phosphorus to sulfur. Is that the nuclear charge is the same as screen remains the same. So sulfur actually has a smaller atomic radius, but phosphorus is first loosely bound electron is found in a 3p sublevel, which is half filled, which is much more stable than sulfur's first loosely bound electron found in a 3p sublevel with 4 electrons, making it much more unstable. Therefore, first ionization so P is atomic radius as extra shell. As a result, P is less firmly held, therefore causes less energy. Yeah. And here's fossil. Yeah, that's exactly what I said. Then we have leaving cert 1996. Bro, how long have we been streaming? Bro, 4.5 hours is crazy. So it says the values of the first 4 ionization energies. The values of the first 4 ionization energies for scandium and titanium, atomic numbers 21 and 22 respectively, are shown in the table. From which electron sublevel A is the first electron lost? B. From which electron sublevel is the first electron lost? The third electron lost. Suggests why the values of the first 3 ionization energies are greater in the case of titanium. They are in the case of scandium. Why the value of the 4th ionization energy is much greater in the case of scandium. Yeah. So first of all, we have scandium and titanium. Scandium having 21 electrons, titanium having 22 electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6. So that's 20, I believe. No, that's 18. 3p6, 4s2, 3d. So that's 2, 2, that's 10. That's 10. So 3d, 1. 1s2, 2s2, 2p6, 3s2, 3p6. This would be a kind of question like, it's nice, don't get me wrong, it's not a bad question, but it's just like, it's just a bit more difficult to grasp, right? So, from which electron sublet is the first electron lost? A would be 4s for both. B would be the third electron lost. And then suggest why the values of the first 3 ionization energies are greater in the case of titanium than they are in the case of scandium. For the first 3 ionization energies are greater for because when the fourth electron, fourth loosely most loosely bound electron was removed from scandium, it was removed from so this is part 2 really. So because when the fourth most loosely bound electron was removed from scandium, it was removed from the 3p sublevel as opposed to the 3d sublevel in titanium as p sublevel is in energy level 3 compared to n equals 4, it requires much more energy to remove electron and then oh I feel like I'm just gonna spiel about. Yes, exactly what I said. The fourth electron in scandium is being removed from an extremely stable and full outermost tree sublevel. Hence, it requires a lot of energy to remove. Oh, this being removed from extremely stable full 3p sublevel So an atomic orbital is the region in the space around the nucleus of an atom where there's a high probability of finding an electron. How many atomic orbitals are occupied? So carbon, remember, 6, not 12. Don't get that mixed up. So 1s2, 2s2, 2p2. So 1s2, 2s2, 2px, 2py. Remember Hund's rule of maximum multiplicity states that when two orbitals have the same energy available, the electrons will fill them singly before filling them in pairs. So 2px1, 2py1. So 4 orbitals. Okay. One atom. Because Heisenberg's uncertainty principle of 1927 states that it is impossible to find both the position of an electron and its speed at the same time, both the position of an electron and its speed at the same time, as the electrons travel in a wave motion. See, half the distance between the centers of two singly bonded atoms of half the distance between the centers of two singly bonded atoms of the same element. State and account for the general trend in covalent radii down group 1. So you know that the atomic radius increases as we go down group 1 as the screening effect of the inner of the electrons in inner completed shells and the outer electrons increases as we go down the group, and therefore the nucleus this screening effect blocks out some of the pull that the nucleus has on the outer electrons. So those outer electrons are therefore less firmly held by the nucleus, and therefore the nucleus cannot pull them towards itself, so larger atomic radius. The bar chart shows the covalent radii 2008 values for the atoms of the elements of the second period. Account for the general trend shown. Period. We know that atomic radius decreases as we go across a period due to increase in the increase in the nuclear charge and the number of protons in the nucleus, and the screening effect of the inner electrons in the inner completed shells and the outer electrons remains the same. So therefore the nucleus finds it easy to attract the outer electrons and pull them inwards towards itself, therefore smaller atomic radius as we go across the period. Define first ionization energy. The first ionization energy is the minimum amount of energy to remove the first loosely bound electron from a mole of isolated atoms of an element in their neutral gaseous ground state. Now, why do first ionization energy values show a general increase across the second period of the periodic table? Second period of the periodic table is because the atomic radius is decreasing as we go across a period. Therefore, the first loosely bound electron in each of these elements is going to be held more closely to the nucleus, and therefore it's going to require more energy to remove the first loosely bound electron. The full set of successive ionization energy values for the electrons in kilojoules per moles and order 1. How does this set of number provide evidence for the number of electrons in the carbon atoms? Because the 6 ionization energies, therefore we know the 6 electrons in the carbon atom. The number of electrons in each main energy level in the carbon. The first two ionization energies are within close range of each other. Then the next two ionization energies are within close range of each other, but they're larger than the previous two values, or are significantly larger than the previous two values. Then the last 3 ionization energies are within range of each other, but they're significantly larger than the other 4 values. In the periodic table, identify an element in the same period as magnesium. In the same period as magnesium, but with larger atoms. Oh, so relative atomic mass number. Aluminium, but with smaller atoms. Sodium. The minimum amount of energy needed to remove the first loosely bound electron from 1 mole of isolated atoms of an element in a neutral gaseous ground state. Explain why the first ionization energy value for silicon is greater than that of aluminium. So first of all, look at the atomic radius. The atomic radius of silicon is smaller than the atomic radius of aluminium, as the nuclear charge is greater in silicon, as it has one more proton, but the screening effect is same in both of them, of the inner electrons in the inner completed shells and the outer electrons. Therefore, the nucleus has a stronger pull on those outer electrons, therefore requires more energy to remove the first loosely bound electron from a mole of silicon atoms, less than that of carbon. Because carbon has a smaller atomic radius, as it has one less energy level, or one less outer shell. Therefore, the screening effect of the electrons, the inner completed shells, and the outer electrons is less. Therefore, the nucleus has a stronger pull on the first most loosely bound electron. Therefore, requires more energy to remove that. And yeah, so the successive ionization energy of silicon is shown in the graph on the right. Because expand the graph between four energy levels in the silicon atom. The first four ionization energies are within close range of each other. Therefore, this suggests that they're all in the fourth energy level, n equals 4. Oh, let's just do it. Silicon. This is actually smart to do this. Silicon has 14 electrons, so 1s2, 2s2, 2p6, 3s2, 3p2. Yeah. So the first four electrons, the ionization energy is in close range of each other, so they're part of n equals 3. So they're being removed from n equals 3. Then the next 8 ionization energies of the electrons removed are within close range of each other, so therefore they must be in part of the same energy level, n equals 2. And then the last two ionization energies are within close range of each other, so they must be part of the same energy. They must have been removed from the same energy level, n equals 1. It's, half the distance between the centers of two singly bonded atoms of the same element. Okay, I think I get ionization energy now. That was easier than I was expecting. We did a few questions. I'm feeling good, feeling hyped. You get me, bro. Elimination reactions involve removing a smaller molecule from a larger molecule, which results in a double bond in a product molecule. So we know one, which is the elimination reaction with ethanol, where we get ethene gas and water. But there's another one. Oh, bro. No. Polyvinyl chloride, but that's vinyl chloride is chloroethene. This stupid as shit, bro. I'm actually gonna crash out. Delocalized electrons are electrons that are free to move between several bonded atoms. Localized electrons are electrons that are located between atoms and are not free to move. I don't know, I'm just kind of Reminiscent, bro. Alright, is there any condition? I don't think there's any condition, but I think it's something like what was I gonna say? Yeah, so it's like a 1,2-dichloroethane. Banana. Okay. So HCC, so 1,2 dichloroethane, and then I'm gonna get vinyl chloride or chloroethene. Remember, removing a small molecule from a larger molecule and getting a double bond in a product molecule, and hydrogen chloride as well. So, reactions as acids, alcohols and carboxylic acids. Oh, what is this shit, bro? Oh, bro, I'm just super, like, just. Oh. So, reactions as acids. So, ethanol can act as an acid, so a proton donor. So, CH3, COOH plus Na is going to give us CH3, COONA plus a half H2. Simple enough, I guess. The hydrogen in the hydroxyl group of ethanol is polar. The oxygen is in delta negative. The hydrogen is delta positive. This allows the hydrogen to break off the alcohol molecule and replace by sodium. Ethanol is extremely weak acid, weaker than water. It only acts as water, extremely reactive metals, so it's alkaline metals. So lithium, sodium, potassium. Why carboxylic acids are acids? Why are carboxylic acids acids? I don't know. I don't know. Alright. If we examine the carboxyl functional group. Yeah, because oxygen is more electronegative. Yeah, we know that. The pulling of electrons away from the OH group towards the carbonyl group is called the inductive effect, and allows the H atom of the, so that bond, that C double bond O, is a polar bond, meaning that the carbon is delta negative, the oxygen delta positive, so the delta positive is going to attract the negative charged electrons towards it. Therefore, it pulls those electrons away from the hydroxyl group. It's like, no, you're not going to get them. That's called the inductive effect. It allows the H atom of the hydroxyl group to be donated, because why not? Hence it's acid. Now, when the carboxyl group, when the carboxyl a carboxyl. C double bond O, single bond O, single bond H. This is a carboxyl group. Oh, but carbonyl group is C double bond. Okay. I get it. When the carboxyl group loses a proton H plus, the carboxylate ion. So when this is lost, it forms a carboxylate ion. The length of C double bond O bond and the CO bond are equal. So the negative charge is not localized but spread over the three atoms, and this configuration gives the carboxyl ion extra stability. So when, let's say, because of the electrons are being pulled away from the hydroxyl group, this is called the inductive effect. Yeah, basically that means that the proton from the hydroxyl group can be donated, right? So when it is, well, let's say it's donated, this forms a carboxylate group. So when a carboxylate group loses the hydrogen, it forms a carboxylate ion, and the length of the C double bond O bond and the CO bond are equal. So the bond length, so C single bond O and the C double, so this is the same bond length, are equal. So the negative charge is not localized. So the negative charge is not only here on the C double bond O, but it's also here as well. So it's spread over the three. Spread over the three atoms, making the carboxyl ion more stable. We talked about magnesium, hydrogen gas. We add 3 centimeters of magnesium rope to a test tube, quarter fill the test tube with ethanoic acid. Magnesium disappears, hydrogen gas is given off effervescence. Sodium hydroxide. A hydroxide is going to give you plus H2O. Oxide hydroxide. So organic synthesis. So now organic synthesis, buddy. Organic synthesis. Describe using equation how ethanoic acid can be synthesized from ethene. So I have ethene, right? How is ethanoic acid going to be synthesized from Okay. H, C, double bond C, single bond H, H, H. So how can ethanoic acid be synthesized from ethene? So carboxylic acid, I'm straight away thinking primary alcohols, stuff like that. So I know if I react this with H2O, yeah, I'm gonna get so if I react it with H2O, I'm gonna get ethanol. This is a primary alcohol which can be oxidized to an aldehyde, which can be oxidized to a. Then I'm like, okay, HCCOH, H, 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 H. Now, how do you oxidize it? You need sodium dichromate 6, sorry. Yeah, so we get methanol. Don't worry, I'll label everything. This is that ethanoic acid? Yeah, ethanoic acid. Yeah. So this is ethene. This is what we call a ionic addition reaction. This forms methanol. Methanol goes to methanol. Oxidation. Methanol, methanol, and ethanol, and ethanoic acid. That's pretty easy. So now we're going to talk about formation of PVC. First of all, what do we need? We need to do ionic addition reaction of ethene with chlorine to form 1,2-dichloroethane, right? So this is just organic synthesis, pretty simple stuff, right? So 1,2-dichloroethane. So this is ionic addition, yeah. So once we've done our ionic addition reaction, we then have elimination reaction. So elimination reaction, removing a smaller molecule from a larger molecule, which results in a double bond in a product molecule. So elimination reaction. Bro, I'm just getting tired, man. But no. No, we grind this shit, bro. We own this shit. Like this. Alright. It's reduced. Bang. No, sorry. It's eliminated to get vinyl chloride or chloroethene. Yeah, chloroethene. C double bond C H plus HCl. Yeah. And then we have the polymerization. Let's say I just say 3 repeating units. I'm not giving up a fight, cuz. Alright, let's just do 2 for simplicity's sake. Alright. I'm just tired, bro. See all of this. I want to do all of these questions, bro. We'll do all of them because we've done all of the stuff that we need to do these questions. These questions will basically, if I can do all of these questions, this will set me up for all the organic questions, which is 50% of the exam. It's gonna be light. Alright, I'll be back. I need to go toilet. I'm gonna sweat on these exam questions. I'm gonna sweat on these exam questions. Come on, come on. All right. So question 1, it says volatile organic liquid was found because it's 66. Okay, carbon 11.11. If the relative molecular mass of the liquid is this, show how the molecular formula C4H8O may be calculated from the percentage composition given above. Oh yeah, I know how to do this. This is empirical formula. So 6.67. Don't doubt yourself, bro. Don't doubt yourself, bro. I'm telling you. Don't doubt yourself, cuzzy. Divide by 1. And oxygen is like 22.22 divided by 16. So let's just get that in now. 66.67. Nice number there. Yeah, me. 5.55583. 11.11. And yeah, it's 20. This is exactly what we need to do. 16, 1.38875. So these are all moles. So this is mole, this is a mole, and this is a mole. 5.55583 divided by 1.38875. 4. So ये 4 ये 1 और ये 8 होगा. I think so. Is it? What? Yeah, I'm coming. Wait, C4 H8 O. says how. Oh, I just have to show how I got this. Okay, so then I have 4 by 12 plus 8 plus 16 is equal to 72. And then 48, 56, 72, 72 is equal to 72, which is true. Describe a test that will allow you to distinguish aldehydes and ketones. Easy. But I have to go eat. But I'll be back. Alright, I'm back. Come on, let's go. Alright, let me drink some water. Describe a test that will allow you to distinguish between aldehyde and ketone. So, add a few centimeters cubed of an aldehyde to one test tube and add a few e.g. ethanol, e.g. propanol, e.g. propanone to another test tube. Now we have three options. We can use acidified potassium permanganate 7 solution. We can use tolerance reagent, so ammoniacal silver nitrate solution, or we can use Fenning's A plus B solution. Add equal volumes of Fenning's A plus B solution to both tubes. Blue due to presence of Cu. Apply heat gently and mix so add a few centimeter cubed of, that's wrong, add a few centimeter cube of unknown, add a few centimeter cubed of unknown solution, so ketone or aldehyde ketone or aldehyde to a test tube. Add equal volumes of Fenning's A plus B solution to the test tube. Apply heat gently and mix thoroughly. If aldehyde present, color will change from blue to red precipitate as aldehyde will reduce Cu2 plus to Cu plus. If ketone present, solution blue. So we added this solution that's unknown. It either contains a ketone. All we know is it either contains a ketone or an aldehyde. We're going to add a few centimeters cubed of this solution to a test tube. Add equal volumes of Fenning's A plus B solution into the test tube. Heat gently and mix thoroughly. Now apply heat gently and mix thoroughly. Then if an aldehyde is present, the color is going to go from blue to red precipitate. Why? Because aldehyde is a reducing agent. It's going to reduce the Cu2 plus, which is blue, to copper plus, which is a red precipitate. Now if the ketone is present, this reduction will not take place. Therefore, the solution in the test tube will remain a blue color. Done. So they keep on asking C4H this one. So it's butanol. No, butanol. Sorry, butanol 2 methyl propanol And then if it's a ketone, it's butanol. Then it says, how would you carry out the reduction of aldehydes and name the products of the reaction? So the reduction, how would you carry out the reduction? So the reduction of aldehydes in 3. So aldehyde, first aldehyde is, how do we reduce? How do we carry out the reduction of an aldehyde? Reduction, so we're not oxidizing, we're reducing. Um, so reagent is H2. Condition is the nickel catalyst. So this is for both. Nickel catalyst is our condition. Now, يعني, how do we do this? How do we do this? How do we do this? So, how would you carry out? So, I mean, I mean, and then what are the products? So it's gonna be, so it's butanol, so butanol, and 2-methyl propanol. That's it. Ketones can be reduced to secondary alcohols. What secondary alcohol? A secondary alcohol is an alcohol which has two carbon atoms directly bonded to the carbon which is bonded to the OH group. Write the structural formula of the secondary alcohol produced by the reduction of a ketone you've named above. So the ketone we've named above is butadiene. So butadiene. So it should be butan 2 no, butan 2 all. Shit. Butan 2 all. Right? So then it says, question 2, it says, what oxidize? Oh, so in organic preparation, students oxidize ethanol to ethanoic acid, so primary oxidation, so primary alcohol being oxidized. Then they warm the mixture of ethanol and ethanoic acid with concentrated sulfuric acid in a test tube. What oxidizing agent would you use? Ethanol to ethanoic acid, sodium dichromate 6. In carrying this experiment, how would you ensure that the main product was ethanoic acid and not ethanol? And how would you obtain a reasonably pure sample? So to ensure that the main product was ethanoic acid and not ethanol is react product, place few centimeters cubed of product into test tube until quarter full. Add approximately 3 centimeters of magnesium ribbon if magnesium dissolves and effervescence is visible. If no excuse me, if no effervescence, aldehyde present. But you know a better one that I would do? Instead of the magnesium ribbon, I would do sodium carbonate. So sodium carbonate is going to give us CO2 plus H2O plus CO2 plus H2O, CO2 plus H2O plus sodium stearate. Yeah. So what that does for us, right? Sodium carbonate is the diagnostic test. We had a few centimeters cubed of ethanoic acid, ethanoic acid to our test tube. We then add a spatula full of sodium carbonate into our test tube, and effervescence is visible due to the carbon dioxide that's given off. And if we bring a lighted taper near the mouth of the test tube, the carbon dioxide would quench the flame. Yeah. Now, write a balance equation for the reaction in ethanol and ethanoic acid. Organic product of the reaction. To which family does the organic product is that? It's an ester straight off the bat. So, ethanol and ethanoic acid. So, ethanol plus ethanoic acid. Remember, the hydrogen of the functional group of the uh, carboxylic group of the carboxylic group of the carboxylic acid is replaced with the alkyl radical of an alcohol. So it's just basically everything's the same as the carboxylic acid except for where you see the hydrogen group and the hydroxyl group. The hydrogen gets replaced by the alkyl radical of an alcohol. Yeah. So, and then it says write the name. So this is ethyl, because ethyl, and ethanoic, and it's an ester plus H2O. Now, is it balanced? I think so. Should be, yeah. Show the structure of the functional group in alcohols. Carboxylic acid. What is an ester? Alcohols is OH. In carboxylic acids, it's an ester is an alcohol. An ester is a carboxylic acid where the H of the functional group of the carboxylic acid is replaced by an alkyl radical of an alcohol. The weakly acidic nature of alcohols may be shown in reaction such sodium. Write an equation between sodium and the alcohol of your choice. So ethanoic acid I think is CH3COOH plus Na is going to give me sodium stearate. So CH3COO. No, not sodium stearate. Sodium ethanoate. Sodium ethanoate. Sorry. Plus a half H2. Name the organic. Oh, sodium ethanoate. An ester containing two carbon atoms in the molecule is prepared by the reaction between carbon. Give the name and the structural formula. So methyl methanoate has to be. It's the only one. Write an equation and give the name and the structural formula. So let's draw it out. Write an equation for the reaction involved in its preparation. Oh, bro, it's basically this. Yeah, it's methanol, yeah? Reacted with methanoic acid, or it's known as formic acid, which is found in sting ants and nettles. See, linking. Yeah. Oh my god. Wait, okay, so carboxylic acid, yeah. So methanoic acid is C double bond O, single bond O, single bond H with H there. And it's got okay, yeah. So then we have the ester, which is methyl methanoate, which is C double bond O, single bond O, single bond C, single bond H plus H2O. The ester is a structural isomer of another carboxylic acid. Probably ethanoic acid. Substitution and addition reaction in organic chemistry. So a substitution reaction is where an atom or group of atoms is replaced by another atom or group of atoms and their two product molecules. An addition reaction is where two different substances react with each other to form one main product molecule. Addition reactions are characteristic of unsaturated compounds. It means contains a multiple bond between two carbon atoms. Show by means of equation a substitution reaction of a named alkane. Name the organic product. Show by means of addition of a named alkane. God, I'm not bothered to do that. I want to do the actual like exam paper questions. So leaving cert. I actually want to do the actual exam papers. I was just doing the workbook questions, but they're based on exam questions, I'm sure. But which one of the three compounds would you expect to be least soluble in water? Alkanes, as they do not form hydrogen bonds with water. Give the UPAC names of the compounds A and C. A. Sorry, that's not even alkene. That's alkene, bro. I just see H6 or A. Give the UPAC names of compound A and compound C. So this is going to be propene. And C is propanone. Name both isomers of compound B. Oh, what the frick? Propanol. Propanol. Yeah. Yeah. Propanol or but I just want to experiment. C, double bond O, single bond H. Can't be that. Could it be a ketone? Uh, 1, 2, 3, 4, 5, 6. No, it can't be. Yeah, no. What other things have a hydroxyl group? Alcohols, they do. Both isomers. Oh, it's just another alcohol. So propanol. So bang, bang. Double bond. Sorry. So C O O H C. So this is 1, 2, 3, 4, 5, 6, 7, 8, 8 hydrogens, 1 oxygen tree. So 2 methyl ethanol. Classify each compounds A, B, C as having 1, 2, or 3 tetrahedrally bonded carbon atoms. Hmm. 2. D would have 3, and C would have 3. Because this 1, 2, 3, A would be a 1 double bond, so it would be unsaturated, and then it would be the 2 single bond. No. Draw it out, bro. I'm telling you. You'll make some stupid ass mistake and you'll be crying when you don't get the grade you want. Yeah? There's only one. Next one, 3. We know that. And next one, 3. No, not 3. You stupid idiot, bro. It's not 3. It's 2. Yeah, but, man, I need to draw these out, man. I'm trying to take shortcuts here. 1, 2. 2. Yeah. Compound C can be synthesized from compound A in 2 steps. With one of the isomers of B as the product. We want to go from propene to. We're going to go from propene to propanol to No, 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 that's actually no. Propanol, right? So C. So this is like the typical one. This is a primary alcohol. What about propan 2-all? So I did propanol. Yeah. And then what about yeah, so 1, 2, 3, 4, 5, 6, 7, 8. Propan 1-all, propan 2-all. The ketone. Propan 2-all to a ketone. Right. But what are we reacting it with? H2O. Yeah. This is propan 2-all. And then I don't wanna oxidize that. So the reagents are gonna be H2O. Then it's gonna be sodium dichromate 6. Compound C is a solvent, so it's called acetone, used in nail polish remover. Oh, bro, I'm stressed out, man. Bro, help me. Draw the structure and give the UPAC name for. Bro, this is the most light thing I've ever seen. This is ethanol, bro. Bro, I did some like weird ass thing, yeah. I didn't even know C-double-bond-O single bond H H H. Yeah. Draw a structure and give the name of the ester with the molecular formula of an ester. Okay, we can go for methyl ethanoate. So C double bond O single bond O C. You pray for needs, I know. No, I studied everything, bro, but I don't know if I'm prepared. So C double bond. So C, yeah, this is it. Done. It's good that I'm doing past papers, but I'm actually really proud of myself. I finally got to the stage. Fine. Woo! You know, which of the compounds A, which of the, which of the compounds A, B, or C has no tetrahedrally bonded carbons? Let's draw out all of them. And instantly, actually, before even drawing it out, A is the answer. But okay, because it's ethene, so it doesn't have. Now, draw the structure of the molecule of this compound. So H, C, double bond C, H. Always draw out the molecules, bro. I'm telling you. Classify the conversions X. So Y is substitution. So going from an alkene to an alkane. X is ionic addition. I'll just say free radical. An atom or group of atoms with an unpaired electron. X, Y, Z. I think it's an. I think this is also ionic addition. First of all, am I tapped? First of all, am I tapped, bro? Because since when can alkene... okay, it's okay. You want to convert an alkene to an alkane, ionic addition. If you want to convert an alkane, Y is a free radical substitution. And Z would be C2H6, which is the alkane. There we go. That's be free radicals. That's ethane. Ethane free radical substitution. No. I'm actually stupid, bro. I can't even get this right, bro. I'm so stupid. X, alkene to alkane ionic addition. I'm getting it right, finally, yeah. Y, which is an alkene to an alkane, a chloroalkane, alkene to alkane ionic addition. And finally, the only reaction involving an alkane is free radical substitution. So alkene to alkane free radical. No. Alkene to alkane ionic. Alkene to alkane ionic. Alkane to chloroalkane. Free radical substitution. What reagent is used to convert A to C? Ionic addition, right? Hydrogen chloride. So HCl, hydrogen chloride. What reagent and what conditions are required for the conversion of B to C? Cl2 and UV light. Describe the mechanisms of the reaction for the conversion of A to C. So first of all, ionic addition. Stage A is going to be the polarization of HCl molecule. Bro, I really struggled with that. Like, just I was juggling it in my head, bro. I just couldn't. I couldn't hack it, bro. So this is it. Area. Now, which one is more electronegative? Chlorine or hydrogen? Chlorine or hydrogen? Chlorine, right? So this is delta negative and this is delta positive. Bro, I'm working overtime, Kazi, bro. So CL, yeah, is what we need to replace. So trace amounts of ethanol. Draw the structure of the UPAC name of an aldehyde with the molecular formula C3H6O. Draw the structure and state the UPAC name. UPAC name would be propanol. Structure C single bond H H. Alright, then it says draw the structure and give the name of another carbonyl compound that has the same molecular formula. Probably a ketone, right? So bang, carbonyl. It has a carbonyl group as well. It's called propanone. Yeah. It's propanone. Oxidized to a carboxylic acid. Carboxylic acid is going to be propanol. So propanol. And it'll be propanoic acid. The diagram shows the arrangement of a glass roof for the extraction of clove oil from the steam. What is purpose of the tube mark X? So tube mark X is used to release pressure to prevent the buildup of steam and to avoid explosion. What is collected at Y? Probably ethanol. No. Clove oil. What is collected at? A milky white emulsion, clove oil emulsion. It's milky white. One use of clove oil is that it's used as a spice in cooking. Now, copy into your answer book the ester shown. Alkane. C is alcohols. Show B to A is an elimination reaction. What do features? Elimination reaction is moving a smaller molecule from a larger molecule, which results in a double bond in a product molecule. Name the reagent catalyst required to convert C to B. To convert A, H2 is the reagent and it's a nickel catalyst. Draw the full structure formulas. Formation of C, Tollens reagent, Felling's test, or acidified potassium permanganate 7 solution. Man, I think we're good. That did my head in a little bit, but I think it slides. Remember I was procrastinating and I did it all in just one day, buying the house. Alright, so kind of getting bored of this shit, but I guess we're gonna keep on going, lads. Ladios. I think I might do the test for the anions. Test for anions, yeah, no, it's anions, because so vaporization, production of positive ions, acceleration, separation, detection. Screw that. And the principle of mass spectrometry is that the different ions are going to be separated based on the different mass or mass charge ratio when moving in a magnetic field. To determine the presence of the different isotopes in the sample, to show the relative abundances of the isotopes of an element, to calculate the relative atomic mass and relative molecular mass, and to identify a compound that if it comes from an unknown source. What do we want to do? There is a chapter which I've been putting off for a while, so I guess we could study that. It's called rates of reaction. Alright, let me get some push-ups in, bro. Feeling ready to go for rates of reaction. Come on, let's do this. Oh. Excuse me. The course is in my hands now. You get me? You get me? It's light, bro. One day, like this, like this, like this, like this. I'm joking. I'm joking. I gotta be humble, man. I'm joking. I'm joking. Chemistry, chemistry, chemistry. That's how you solve anxiety. You don't wait around like I'm not gonna be able to do it. You just get it done. Bro, all waiting around is just like done for me, bro. It's like nothing in my life, absolutely nothing. It just leads to pain and anguish and agony, bro. Rates of reaction is the most bullshit chapter ever. Rates of reaction. The rate of a chemical reaction is defined in the change in the concentration per unit time of any one reactant or product. So, rate of reaction. So the rate of reaction of a chemical reaction is defined by the change in concentration per unit time of any one reactant or product. Reaction. Change in the concentration per unit time of any one reactant or product. Alright. First of all, we have to look at the. My water's kind of running now. I can't lie still. But... yeah. Change in concentration per unit time of any one reactant or product. So there's 5 factors that they're going to affect rates of reaction. There's 5 factors that affect the rates of reaction. First of all, the nature of the particle, the nature of the reactants. So are they either ionic or are they covalent? So we'll do that later. We'll do these chapters. It's atomic theory 8, 9, and 10. We'll do them. Let's have to do spectrometry. Is it called? What is it called? Paper chromatography. I know I always mix up colorimetry and chromatography. They're not even the same thing. The only time in the course we look at colorimetry is in water with a chlorine-free DPD and the comparator box and the color disc, and you spin it around in the light. You see until the colors match and reach the reading in parts per million. It's deionized water of equal volume. Yeah, okay. Nature of reactants: ionic or covalent. The particle. The particle size itself, when one of the components is solid, because of course particle, yeah. 3 would be concentration. That's the definition. Concentration, temperature, and catalyst. So the nature of the particle is it ionic, is it covalent? That's intramolecular forces of attraction. Then what else was it? Temperature, concentration, catalyst, and then the physical size of the particle if one of the components is solid. So the nature of the reactants, right? In general, ionic reactions are faster than covalent reactions. In ionic reactions, all that is required is the coming together of ions that are already present in the solution, so it is quick. In covalent reactions, bonds have to be broken and new bonds have to be formed again, so no more time is needed. An example of ionic reaction is when a solution containing silver plus ions is added to chlorine minus, an immediate white precipitate of sodium chloride is observed. An example of a covalent reaction is the reaction between sodium thiazide and hydrochloric acid. So the reason why ionic compounds, right, ionic reactions, sorry, they occur much faster than covalent reactions because those ions are already present in the solution, they just come together bound before the new substance. In covalent, electrons are being shared between atoms, so the bonds have to be broken, the new bonds have to be formed. So yeah, it's much slower. Then we have particle size as well, yeah. So in general, the larger the particle size, the slower the reaction, because we want smaller particles. So for example, let's say you have a potato. Let's say you're boiling a potato. I'm just giving my own analogy, right? You boil a potato. It's going to take longer if you cut it up into smaller pieces and you boil it because you're increasing the surface area because the surface area is smaller. If the particles are smaller, the reaction rate will greatly increase. If very finely divided particles are used, so very finely divided particles, a dust explosion may happen. If a powder called lycopodium powder is placed into a tin with a lit candle and powder is blown over the candle, explosion can occur which will blow the lid off the tin. In order for a dust explosion to occur, dust explosion requirements, I guess you could say. So the requirements of a dust explosion, finely divided, the particles have to be finely divided, combustible, which means they burn oxygen to form H2O plus CO2, dry, yeah, oxygen present, because you need that, yeah, and combustible, and then it has to be an enclosed space, and there has to be a source of ignition. So the particles have to be finely divided, they have to be dry, they have to be in an enclosed space, they have to be combustible, there has to be a source of oxygen, and there has to be an ignition source as well, source of ignition. Then we looked at experiment. An example of how particle size can affect a reaction can be seen in reaction between calcium. In general, the greater the concentration of the reactants or just one of them, the faster the rates of reaction. This is because if the reactants are present in large concentrations, then there is a great chance of them colliding with each other successfully. Large concentrations, greater probability that they'll collide with each other successfully in a short space of time. If the concentrations of the reactants are decreased, then the successful collisions take longer to happen. Temperature. As mentioned above, the number of successful or effective collisions determines the rate of reaction. So successful or effective. If the temperatures increase, the molecules have more kinetic energy, therefore they're more likely to collide often with each other, thereby they will collide more often with each other, therefore increase the rate of reaction. Usually increase temperature by 10 degrees, double the rate of reaction. Question: how does a small rise in temperature lead to large increases in rate of reaction? Come today. Catalyst. As we have already seen in the first experiment, the presence of a catalyst can greatly increase the rate of a chemical reaction. So an example of how particle size, this particle size. So 20 grams of large marble chips in a conical flask and 50 centimeter cube of known concentration of hydrochloric acid in a graduated cylinder are placed on an electronic balance separately. Some cotton wool is placed in the mouth of the conical flask. The total mass of the apparatus and the substances are noted. The plug is removed. The acid is then added quickly to the flask, and the cotton wool plug is placed in the mouth of the conical flask. To prevent any shade from escaping, the empty graduated cylinder is replaced on the balance. The stop clock is started immediately. The mass is then recorded every 30 seconds, so we get 3 consecutive results that are the same. The loss in the mass is due to carbon dioxide being lost to the cotton wool plug. The loss in mass can be calculated by subtracting each mass from the initial mass before the reaction was started. A graph of loss in mass against time can be plotted. This experiment was then repeated using the same mass of a smaller marble chip and the same volume and the concentration of acid. To be honest, temperature catalyst. Activation energy is the minimum amount of energy needed. Is the minimum amount of energy that colliding particles must have in order for a reaction to occur. Of course, I want to be able to do this question in the exam, but can't lie, it just looks like a lot of effort for not much reward. I mean, one whole question actually is quite a lot reward, but the rate of a chemical reaction is the change in the concentration per unit time of any one reactant or product. Why does the rate of chemical reaction generally decrease with time? I can't lie, I'm kind of exhausted, bro. Six hours is crazy. What the hell? I haven't studied for 6 hours. Maybe like around 4.5, 5 maybe 5 hours probably. I need to do rates of reaction somehow, some way, somewhere, some methods. I don't know how I'm gonna do it, but I don't know why I find it so hard, bro. Why is it such a hard chapter, bro? It's not hard. It's just long. Like it just. I don't want to learn no theory about this crap and that crap. I'm just gonna have to do it, bro. I think I'm just gonna have to suck it up and just do it. The larger particle size, the slower the rates of reaction. The smaller the particle size, the increase in the surface area, the faster the rates of reaction. When the plug is removed, the acid is then quickly added to the flask, and the cotton wool plug is placed in the mouth of the conical flask, just in the escape. Loss of mass in grams in time. So it increased the rate of chemical reaction. And monitoring the rate of production of oxygen from hydrogen peroxide using manganese dioxide as a catalyst. So, monitoring the production of oxygen from hydrogen peroxide using manganese dioxide as a catalyst. So, oxygen production from hydrogen peroxide using manganese dioxide as a catalyst. So, H2O2 is like MnO2, and we get H2O plus a half O2. Now we have this. You know what I'm gonna do? Because I kinda hate this chapter, what I'm gonna do is I'm gonna open another tab of this. And let me just close the rest of my windows on my computer because I have so many things open right now. Right. So what I'm gonna do is I'm gonna open up another one of these. I'm gonna put it on the exam paper questions. So I'm gonna look at the exam paper question, whatever I can't answer, I'm gonna go back and I'm gonna learn that. And I think that way I'll be like unstoppable, bro. Alright. I'm gonna just put this on the right hand side like this, and then I want this here. Yeah, so a catalyst is a substance that alters the rate of chemical reaction was not used up. So catalyst. So we have a Worksheet. Uh, 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 so rate of reaction is the change in the concentration per unit time of any one product or reactant. And the activation energy is the minimum amount of energy particles the minimum amount of energy that colliding particles must have. So it's the minimum amount of energy the colliding particle must have for a chemical reaction to occur. Draw an energy profile diagram from an endothermic reaction. Oh, what do they do to the activation energy? Catalyzed, the activation energy is going to be lower. Is lower. Oh, bro. Endothermic. Uh, energy and of direction of reaction. So endothermic they're gaining. So this is my like reactants. This is my products. I don't know if that's even right. Endothermic, and exothermic. Yeah, direction of reaction energy. Yeah. Oh, bro, I just feel so tired, man. This is the non-catalyzed reaction, and this is the catalyzed reaction. So it can be shown kinetic theory of gases. A 10K rise in temperature increases the collision by only about 2%. I mean, higher temperature, the molecules have a higher kinetic energy, therefore they're more likely to collide with each other. Suggests the reason why a much greater increase in number of suggests a reason for the much greater increase in the reaction rate. Is a greater proportion of the molecules will have an activation energy. So an increase in the kinetic energy of the molecules and a greater proportion of the molecules will have activation energy. So a greater proportion of the molecules that have active. A catalyst is a substance that alters the rate of reaction without is a protein that alters the rate of reaction without being used up itself in the reaction. This just seems so slow, bro. I don't think it's the right time to do this chapter, bro. I don't think so. I think I might just do some Irish, cause yeah, right now I'm just too tired for any of the other stuff, bro. I'm gonna just do some Harlamabach. Just call it a day, bro. Because I ate his food, bro, and it just makes me sleepy, man. Harlamabach, 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 Harlamabach. Okay, guys, I'm gonna try and energize myself. Oh, so Harlamabach. So is I Lishin Priv character on Gash Del Shah. So Lishin is the pre. Okay, let me just change the. Okay, so Irish. Okay. So is I Lishin Priv character on Gash Del Shah. Tugtar Largus Dune. Tugtar Largus Quimsog Spatial Dune. So we given. Why is she speaking so? This is what happens, man. This is what happens when you mess up, bro. We were given a comprehensive Tugtar Largus Quimsog Spatial Dune on Kinal Size Dinner on no a character agus an cinál saoil atá ací. Is í lísin príomh character an gghearcéil seo. Tugtar largus cuimsitheach spéisiúil dúin an 6 saoil atá ací an cinál duine atá no dúin ar a character agus an cinál an cinál 6 saoil atá ací. Is duine é dahan í, she's like selfish. Cuireann si béim iri chuann si béim iri sóna an til agus a bhóragas. Déanann si fálaí na rudaí atá níos tábhachtaí agus níos luach maire gosú le saoil an teile. So is í lísin príomh character an gghearcéil seo. Tugtar largus cuimsitheach spéisiúil dúin ar a character agus an 6 saoil atá ací. Agus an 6 saoil atá ací agus an cinál saoil atá ací is duine é dahan í. Cuireann si bé mór ar iri sóna an tail agus ar a bhórachas. Déanann si fálaí ar na rudaí níos tábhachtaí agus níos luach móire cosúil le saoil an teaghlach. So is í lísin an príomh character an gghearcéil seo. Tugtar largus cuimsitheach spéisiúil dúin ar a character agus an cinál saoil atá aici is duine é dahain í. Chuir si bé mór iarraí sóna an tail agus ar a bhórachas, déanann si fáilní ar na rudaí níos tábhachtaí agus níos luach mór sa saoil cosúil le saoil an teile. Bro, I don't know how I did that, bro. Alright, tá féin omh an tábhachtach do lisin. Tá grúig ada ion orthaí, tá si tanaí dáthúil agus furfa. Tá cuma óg orthaí. Níl creidfa aon duine dar leis úsal me gan go bhfuil lisin fiche bliain pósta. Tá féin omh an tábhachtach do lisin. Tá grúig an ada Tá grúig ada ion orthaí, tá si tanaí dáthúil agus furfa, tá cuma óg orthaí. Ní creidfa aon duine dar leis úsal me gan go bhfuil lisin fiche bliain pósta. Is léir go bhfuil teach bra le gardín aici. Tá gach rud gláán agus neart a péin nua ar na málaí, snás ar na huairleoir agus blahannas na proci. Tá lisin an bhóidú is léir go bhfuil si ag iarraidh an méide tá baint amach aici sa saoil le ceilere agus a léir go hoscailtá den dabhain mór. Is maith le lisin nuair a bhíonna is a gine cuairsa go mbíonn si go nóthach sa saoil. Ní gádaí dul amach ag obair in éon cuairt tá baint aici le mór an clubanna. I just feel like sleeping, bro. I can't lie, bro. I'm so tired. I might have to take a break, I won't lie. This Prism Live thing is like a laggy as frick. It's very laggy. Yeah, this shit is cooked. Why is it so laggy? It's freaking laggy, bro. What the hell? Droid Cam is so much better. Yeah. Okay. Oh. It's on the wrong Wi-Fi network. Hello? 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 Is it connected? Bro, for some reason I don't see anything. That's why it's so laggy, man.
Apparently it's unlikely to come up. Rates of reaction. I didn't do rates of reaction. Well, I can't lie. I guess I don't have the brain power to do it. It seems easy. It seems easy. I might do it in the days between the exams. You know, like the days that we have between. Alright, you know what? I'm gonna go for shifts number 2. Let me just actually no, screw Irish for now. Let me just go property. Let me just change it back to chemistry. We're gonna grind chemistry. Just let me go fill up my water bottle and we'll do this. Come on, let's do it.